Morning. Right. So please kindly confirm audio video on screen once. Okay. So let's continue with the previous class which we discussed. Today will be the last class. Today we will be winding up the syllabus as a whole. Right. So we left with only this topic. Yeah. Yeah. So let's continue. So till now we discussed about Slack bus, right? So we have discussed about the Slack bus till now. Now we are going to think about the remaining two buses what we have mentioned. One is a generator bus, next one is a load bus. Yeah. So first I'm going to take the second type of bus, as I said just now. It is a generator bus. Generator bus. See, generally, as I said you earlier, at each bus in the four quantities what we have, so-called P, Q, mod V delta, in these four quantities, definitely we should give two quantities in the data. Remaining two quantities we try to find from the solution of the what we call load flow equations. Yes or no? See, particularly in case of generator bus, we are capable to maintain the real power output as constant in the study. We are capable to maintain the real power output as constant in the study. That's what I said earlier, because each generator should say how much amount of power they demand. Yes or no? Right. Along with that, by using excitation control at the generator location, we are capable to maintain this terminal voltage also as constant. So in that perspective, what I was interested to say is, at the generator bus, generally, real power and magnitude of voltage might be mentioned. Remaining two, what we have, Q and delta, that we have to calculate obviously. Okay, so I can say real power, mod V, these two are known values, or you can say specified values. See, one thing, please, you remember this one. Except at the slack bus, at all other buses, we know the real power value. Except at the slack bus, at all other remaining buses, we know the real power value. So real power is known, obviously. Delta will be definitely unknown, because we have assumed the slack bus as a reference angle, 0 degree. With reference of that slack bus, we have to find out angle at all other buses in the system. Means obviously delta will be unknown number. But at the generator, we have an excitation control. That's why we are assuming mod V as known value or constant value. Okay. Remaining two quantities, Q and delta, we feel them as unknown, or you can say unspecified. Unspecified. Unknown, or you can say unspecified. Okay. See, two known values we have now. Two known values we have. So P and V. Hence, this bus is going to be called as generally PV bus. PV bus in the sense, the bus at which you know real power and voltage magnitudes are known. Real power and voltage magnitudes are known. Okay. Third type of bus, as I said earlier, that is a load bus. Load bus. Yeah. See, already we mentioned maybe in the assumptions, I think, load is going to be represented as constant real power withdrawal. Load is going to be represented as constant real power withdrawal, or we can say constant PQ load. Constant PQ load. So hence, at this load bus, definitely they should mention what are the values of the real and reactive powers absorbed by the load, right? Known values, or you can say specified values here. Specified values, whereas obviously mod V and delta, these two are unknown numbers. Mod V and delta will be unknown numbers. Can anybody tell me what we call this load bus? What's the other name we can give for load bus? Anybody tell me please? Any other name we can give for load bus? Load bus. Already you know real and reactive powers at this bus, right? So according to the known values what we have, so this bus can be called as PQ bus. This bus is going to be called as PQ bus. Okay. Yeah. So let us think a little about the generator bus from this point. we are going to think about the generator bus now. So I'm moving in the next slide. I'm taking up this as an example. We have a generator bus basically. Generator bus. Just listen to my words. Listen to my words. The generator existing at this bus connected to one big power system network, like this. That's the network. And we have some mechanical input given to this generator. And there is a field excitation provided to the rotor field winding. And this field is excited by means of DC voltage source like this. DC voltage source. Okay. And carrying some field current of IF. That winding is carrying a field current of IF. Okay. Next thing. Induced EMF in the stator of the machine is mod E. Induced EMF in the stator of the machine is mod E. Terminal voltage I am showing as mod V. Terminal voltage of the generator I am showing as mod V. Mod V. Okay, next. This bus means this generator is injecting some real power P as well as some reactive power Q into the bus. This generator is injecting a real power of P value, reactive power of Q value into the bus. Simple. I didn't said any new thing here. Just field current, induced EMF, terminal voltage, real and reactive powers P and Q. And this voltage might be having an angle of delta with respect to reference. With respect to reference, we have an angle of delta here. Okay, next. Listen here. See, as we said earlier also, at this bus, terminal voltage is going to be maintained as constant. By what? I'll write here. Mod V can be maintained as constant. By controlling mod E, so-called induced EMF in the stator. By controlling that value, we are capable to maintain the terminal voltage as constant. Okay. How to control this mod E value? By controlling the field current. Or you write by controlling field current. IF. By controlling field current. Okay. Kindly listen my words once. Okay. Yeah. Listen here. See, actually, my intention is to tell you here, what is the reactive power equation Q? What is the equation for the reactive power Q? For example, you assume this generator might be having a reactance of X. I am writing the Q equation. Directly I am writing. I am not going for any derivation. Already we discussed some derivation about the Q. So this will be coming like mod V by X into mod E minus mod V. Like this you will get. Just listen to my words. Mod V by X into mod E minus mod V. Approximately, by neglecting the angular difference between these two voltages. For time being, accept this equation. Right? This equation will come again in T&D. Just follow this one. Q is approximately equals to mod V by X into mod E minus mod V. Okay, listen. I'm recalling the things. Mod V can be maintained as constant by controlling the value of induced EMF in the stator or by controlling the field current. Can we control this field current for any extent? Means, can we keep this field current as 0 amperes? Or can we keep this one 1000 amperes? Can we keep this one 5000 amperes? Or can we keep this one negative value? Is it possible? That's the thing what I am asking. Tell me please. Field current. Can we control the field current for any value you want? No. Definitely, there will be certain limits existing on the field current. In that range only, we are capable to control the field current. Okay. So that statement I am writing now. generally there exist some limits on field current control. Some limits on field current control. Field current control. Like we have IF minimum, IF maximum. Showing here IF minimum less than IF max. IF minimum to IF maximum. Like this we have. Next thing. Next. Listen, please. Next. See, whenever this field current is having certain limits, definitely the induced EMF will have some limits. Yes or no? Because induced EMF depends directly on the field current value. If the field current is increasing, induced EMF will increase. If the field current is decreasing, induced EMF will decrease. So definitely there exists some limits on the induced EMF in the machine stator also. Like this, we can have some limits. E minimum to E maximum. E minimum to E maximum, we have some limits. Okay, next thing. Let us look at this Q equation now. Q equation. Whenever we have some limits on that induced EMF, definitely can we expect some limits exist on the reactive power? I need your response now. I need your response. As we have some limits on the induced EMF, can we say we have some limits on the reactive power also? Yes. Means my intention is to tell you whatever the physical generator or practical generator we have, that generator can't supply any amount of reactive power you want. It can't supply any amount of reactive power you want. There will be some limits existing on the reactive power generated or supplied by the generator. Okay. So I can say, therefore, we have some limits on the reactive power generated by the generator. So you write the statement now. Therefore, at generator bus, there exist some Q limits. There exist some Q limits. Okay. There exist some Q limits. Within that range only, that generator is capable to supply the reactive power. Okay. I'll tell one simple example now. Simple example. Just listen to this example. I am showing in the next slide. I will be showing in the next slide. Simple example. Look here. For example, a generator bus have Q limit cells. Just take this one. Minus 10 MVR less than or equals to Q less than or equals to 30 MVR. A generator bus is having Q limits like minus 10 MVR less than or equals to Q less than or equals to 30 MVR. What is minus 10 MVR? We should feel minimum amount of reactive power it is capable to deliver. Minimum amount of reactive power it is capable to deliver. And this 30 MVR is a maximum amount of reactive power it is capable to deliver. Maximum amount of reactive power it is capable to deliver. Okay. QG minimum and we have that QG maximum. Kindly listen. Listen to me. The meaning of this statement is simple. I am repeating the same thing, but still I am saying again. If the reactive power required to be supplied, listen to me. If the reactive power required to be supplied by the generator comes in the range of minus 10 to 30, then the generator is capable to maintain the terminal voltage as constant. Okay. So else, if the Q to be supplied by generator, within the limits, then mod V can be maintained as constant. Okay, same statement, whatever I said, I am repeating here. Okay, next thing. Listen, please. Listen. One more word I am saying. Just listen. If the Q required to be supplied, please listen. For example, for the same thing, if Q required to be supplied is equals to 40 MVR, what I should say now? If the Q required to be supplied is 40 MVR by the generator, what I should say? See, on the paper, you can write by calculation, you can write that the generator has to supply a reactive power of 40 MVR. That type of statement you can write on the paper. But practically speaking, whatever the generator you are discussing now, that is having a capability of supplying only 30 MVR maximum. Beyond 30 MVR, it can't supply. The generator can't supply. At the time, what we have to do is, we will be making the Q to be supplied by the generator equals to the maximum limit only. We don't say 40 MVR. It will be set to the maximum limit what we have, that is 30. Following all of you. Then QG set to 30 MVR in bracket maximum limit as constant. Okay, please kindly listen to me. What I am saying you. If you are setting that QG to be constant at 30 MVR from this point onwards, whatever the bus we are discussing now, maybe this one, whatever the bus we are discussing now, at this bus, real power already constant, I said. Yeah, I need your response, please. Reactive power to be supplied by the generator is becoming more than the QG maximum. Okay, which is violating the limit. At that time, what I am doing is, I should make this Q to be supplied by the generator equals to maximum value. Okay, so from that point onwards, Q will be constant. P is already constant. Q is constant now. What about mod V? Is it possible to maintain that mod V as constant? No, it's not possible, right? We don't have a control now. So we can't maintain that mod V value as constant from this point onwards. Means mod V value will change. How much is that mod V value new? That we have to calculate by using load flow analysis. Already I know delta value we have to calculate. Not only delta, now we have to calculate the value of mod V also. Tell me now, which are the known values and unknown values in this situation? What are the known values and what are the unknown values here? P and Q, known or unknown? Known values. P is already constant. Q value we are setting to the maximum limit. Okay. And what about V and delta? V and delta are unknowns. V and delta will be unknown. What type of bus is that now? PQ are known, means it's a PQ bus, or you can say load bus. So this is a way, how the people will say generator bus was converted into load bus. When it will be converted? Whenever the reactive power limits at the generator bus got violated, at that time we have to set the Q value to the violated limit, and then we have to convert that bus from generator bus to load bus in the further study of the load flow. So I think all of you understood the statement. So I am writing that statement now. Just observe. If reactive power limits, Q limits at generator bus got violated, if Q limits at the generator bus got violated, then Q supplied by generator set to the violated limit, and that bus, that generator bus was converted into load bus. Generator bus was converted into load bus. Else, you say in a better way, PV bus converted into PQ bus. PV bus converted into PQ bus. PV bus converted into PQ bus. Yes, Sai Charan Reddy. Q required will not be in the QG range. Because if the Q required is out of the QG range, the generator can't supply. Na? At that time, we have to set the Q value to the violated limit. For example, if it's coming below Q minimum, set the Q value equals to Q minimum. Set the Q value equals to Q minimum, and what we will change from the point onwards, and the bus is going to be converted to PQ bus. And if it's crossing Q maximum, set to Q maximum. That's it. Okay. Similarly, is it also like a generator is regarded as a load? Theoretically speaking, it's a load bus, right? Mathematically speaking, it's a load bus. Set means that's what I said. QG, we have to make it equals to QG max. If, for example, I'm saying here, if Q required is greater than QG max, if Q required is greater than QG max, then what we are saying is set Q equals to QG max. That's the meaning of this set. Q equals to QG max, and convert PV bus to PQ bus. PV bus into PQ. Convert that PV bus into PQ bus. Okay, done. Next thing. Similar to this one. Generally at the PQ buses, so-called at the load buses, we have some voltage magnitude limits. At the load buses, we have some voltage magnitude limits. Okay, that statement I will write. This is not much important. To discuss about the voltage limits. Q limits is very important with respect to examination, and we will practice it also. But voltage limits generally we don't practice, just for the sake of examination if you want to remember this. Okay, so at load bus, generally voltage magnitude limits will exist. Mod V limits will exist. Okay, mod V limits will exist means then generally this mod V value will be in the range of mod V minimum to mod V maximum. Mod V minimum to mod V maximum. Okay, so if the voltage limits got violated at the PQ bus, then we have to convert this PQ bus into PV bus by making mod V value equals to violated limit. Okay, right. So if mod V limits at PQ bus got violated, then set mod V to be equal to violated limit, and what we should do, and convert PQ bus to PV bus, because mod V will be constant from the time. So the bus is going to be called as PV. Convert PQ bus into PV. PQ bus into PV bus. Yeah. So as I said earlier, this we don't practice many times in the calculations, but Q limits violation and all we practice many times in the calculations. Yeah. Next thing. These are the two statements you have to remember. Next, I will tell in some other way, some more discussion I want to make. So I'm moving ahead in the next slide. Okay, for example, just listen to me. This is one big power system network we have. This is one big power system network. We have done the load flow. Assume that we have done the load flow. Just listen to my words. Already we have done the load flow. After completing the load flow analysis, I am observing the voltages. At the bus 1, 2, 3, and so on up to n buses we have. At these buses, I am observing the voltages, particularly at some bus number I. At some bus number I, we have some number of lines connected, something like this at this bus. At this ith bus, I am observing that magnitude of voltage is very, very low number. Low number, something like 0.85. Repeating the term, kindly observe my words. Consider these things. Load flow analysis was already done. After completing load flow analysis, I am checking the voltage magnitudes at each and every bus. At the ith bus particularly, I am observing that voltage magnitude is coming like 0.85 per unit, which I feel very, very low in number. I feel that very, very low in number. Tell me now, how to raise this voltage magnitude generally? How to raise that voltage magnitude at the ith bus? We are experiencing very low value. How to raise that voltage magnitude? We have to keep some shunt compensator at that bus. Yes or no? So we have to keep some shunt compensator at this ith bus, something like this, such that this compensator will inject a reactive power of QC. That compensator will inject a reactive power of QC. Following all of you, QC, such that my target is to make this voltage to be equal to 0.96 per unit. I want to make that voltage to be equals to 0.96 per unit. I am asking you very, very simple question. Very, very simple question. Just answer me. At the ith bus, we are experiencing voltage magnitude very, very low. Now, we have decided to keep some compensator at that bus, which has to inject a reactive power of QC, in order to maintain that mod VI value as 0.96 per unit. Increased value we have to maintain. How to calculate this QC number? How to calculate the rating of the compensator QC? That QC is unknown, na? How to calculate the QC value? To calculate the QC value, we should conduct load flow one more time. To calculate the QC value, we should conduct the load flow analysis one more time. Listen please, listen please. See, while we are doing that second time load flow, ith bus what we have now can be treated as what? So please tell me. So what type of bus we should treat this one? Q is unknown now. Q we have to calculate by doing load flow. But mod V is known 0.96. That is our target. That's our target. So voltage magnitude is known. Q is unknown means what type of bus is that? PV bus. Because I know already at all buses except slack, you know the real power value. So P is known already. Mod V is also known here. So obviously this bus is going to be called as PV bus while you are doing the next to load flow. Okay. See this bus we are going to name as voltage control bus. Voltage control bus in the sense the bus at which we keep some reactive power compensator in order to control the voltage magnitude within the prescribed limits. Okay. So I'll say in the next slide. That bus is going to be called as voltage control bus. That's the fourth one. Fourth type of bus. Voltage control bus. Yes, else. This bus can also be called as reactive power control bus. This can also be called as reactive power control bus. Okay. Yes, this can be called as SVC. It's a FACS device actually. Static wear compensator. Static wear compensator bus. Else you can call this one as STATCOM bus. STATCOM bus. See, please kindly listen. This term is very, very important to observe. Control. If there is a control over the reactive power or voltage magnitude, then only that bus is going to be called as voltage control bus here. Okay. So at this bus, P mod V, these two are known numbers or specified values, you can say, and remaining two will be unknown numbers. Remaining two values will be unknown numbers. So this voltage control bus can also be called as PV bus. This voltage control bus can also be called as PV bus. Voltage control bus can also be called as PV bus. Yeah. So I think all of you getting this one. All of you getting this? So what are the different types of buses we have now? Just recall the things. Slack bus, generator bus, load bus, voltage control bus. Okay, mathematically speaking, only three. Mathematically speaking, three. Slack, PV, PQ. Slack, PV, PQ. Okay, so let's discuss some simple problems on this one. SVC means static wear compensator. SVC means it is static wear compensator. It's a controlled reactive power equipment, controlled reactive power injection equipment, FACS device. By means of power electronic controllers, we are going to control the amount of the reactive power injection. Yeah. So let's look at this problem once. Just it's a very simple one. Just say this. Yeah. Go through this question once. Go through this one. A 200 bus power system network has 30 buses with generators. Kindly observe the words. 200 bus power system network has 30 buses with generators, 100 buses having load substations. Means 100 buses are loads you can treat. 100 buses are having load substations in the sense 100 buses are having loads you can treat. Next, 10 buses with fixed shunt capacitor banks. We will take up that word. 5 buses have SVCs, static wear compensators. 3 buses have STATCOMs. 5 buses having fixed shunt reactors. And remaining buses are interconnection buses in the system. Interconnection buses in the sense intermediary buses. Means at that bus, we don't have any load as well as we don't have any generator. Such type of buses definitely exist in the system. That's the meaning of the interconnection buses. Okay. If the number of slack, PV and PQ buses in the load flow are X, Y and Z respectively, the values of X, Y and Z will be how? What is the value of X, Y and Z? That's the question. Yeah. Kindly observe now. Kindly observe from the data what they have given. Just look at the solution. Total number of buses, how many we have? 200 buses. Total number of buses, how many? 200. Okay, next. 30 buses having generators. Now, see, listen please, listen please. He didn't mention anything about slack bus in the problem. He didn't mention anything about slack bus in the problem. If it is the case, one of the generator bus we should treat as slack. Remaining buses will fall in the category of PV. 30 buses having generators, right? So one in that we should keep in the slack. Remaining 29 will come in the category of PV buses. Okay. So slack bus, we have 1, and PV buses, we have 29 now. PQ bus also I will write. Let me count. Okay, next thing. Listen please. 100 buses having load substations. 100 buses having load substations means obviously it will fall in the category of PQ bus. 100 buses having load substations means PQ bus. Next thing. 10 buses with fixed shunt capacitor bank. Fixed shunt capacitor bank will be treated in what category? Is it a PV or PQ? Fixed shunt capacitor bank, is it a PV or PQ? It will be a PQ bus. It's not PV. It's not the PV bus. What's the reason is simply you are saying it's a fixed shunt capacitor bank connected with that bus. You don't have a control over the reactive power. You don't have a control over the voltage. Just we are connecting one capacitor at that bus. That's it. We don't have a control. As it don't have any control, it is treated as a simple shunt impedance. It is treated as a simple shunt impedance connected at that bus. So the bus is going to be called as PQ bus. Kindly remember this word. Kindly remember this word. How many? 10. So I will add 10 here. These are fixed shunt capacitor banks. Fixed shunt capacitor banks. 10 buses. Next thing. 5 buses having SVC. SVC means there is a control. So it will be treated as PV bus. 5 buses are having SVCs. SVC buses, you say? SVC buses. 3 buses having STATCOMs. 3 buses are having STATCOMs. STATCOMs. Next. 5 buses with fixed shunt reactors. Fixed shunt reactor means which bus now? Fixed shunt reactor means which bus? PQ. Fixed shunt reactor means it is PQ. Fixed shunt reactors means it's also PQ bus. So now what are the remaining buses existing in the system? The remaining buses, how many? Count up this number, how much you get, this total, and from 200 you have to subtract that number in order to get the remaining buses. Please tell me how many interconnection buses? It's 1 plus 29 plus 5 plus 3 plus 100 plus 10 plus 5. So it's 153 as a total. So 153 as a total, 200 is the total number of buses. Remaining buses 47. Remaining buses 47. Yes or no? Remaining buses will be 47. 47 buses, in which category we should keep now? 47 interconnection buses we have. Interconnection buses. Which category we should keep that? 47 buses. Is it in the category of PV or PQ or slack? Which category we should keep? See, actually, at this interconnection bus, as we are saying, listen please, listen all of you. Listen all of you. This is some interconnection bus you consider. Okay, this is an interconnection bus. Very simple question I am asking you. Do you have any generator at this bus? Do you have any generator at this bus? Yes or no? Yes or no? Do you have any generator at this bus? No. Means can I say generator complex power equals to 0 at this bus? No generator means generator complex power equals to 0. Do you have any load here? Do you have any load? No, we don't have any load. As you don't have any load, SB value will be 0. Complex power demanded by the load is also 0. Now tell me please, what is the net real power injection and what is the net reactive power injection at this bus? What is the net real power injection and net reactive power injection at this bus? Tell me please. Both values are 0. Generation minus demand. Generation is 0. as well as demand is also 0. So net real for injection 0, net reactive for injection also equals to 0. Net real and reactive for injections are 0. Means, do you know both P and Q values now? Tell me please. Do you know both P and Q values? Nobody is responding. Yes or no? Yes, we know both P and Q values. So this bus is going to be treated as PQ bus. Okay. So this is going to be treated as a PQ bus while we are doing the load flow analysis. So whatever the 47 interconnection buses we said now, that will fall in the category of PQ buses. PQ buses, interconnection buses. Okay. Let's think about the total numbers here. Slack bus is anyhow 1, and this will come 32, 37. Is it 37? And it is 162, I think. 162 PQ buses. Okay. So what's the correct option? What's the correct option here? Just think back. 137, 162. So option B is a correct one to be selected. Correct answer from the options will be B. Option B is a correct one to be selected. Okay. Next. Next thing. So I'm taking up one more question. Just observe this one. It's also simple one. It's a bus 1. Bus 2. So bus number 3. It's a bus 4. Okay. So I'm giving the known values here at these buses. Bus 1, PG 1, QG 0.5. Bus 2, PD 1, mod V 1.05. Bus 3, mod V 1.1, delta 0 degree, PD 0.5, QD 0. And at this bus, PD 1, QD 0.2. Like this we have 4 buses we have in the system. 4 buses. Consider the following system. Consider the following system. And do bus classification. Do bus classification. Do bus classification is nothing but we have to tell what type of bus is each one. What's the bus 1 type, bus 2 type, bus 3 type, bus 4 type. That's the thing you have to answer. That's the thing you have to answer by looking at the data. By looking at the data. What type of bus is 1? Is it a slack, PV, PQ? Similarly, bus 2, bus 3, bus 4. That's the thing. Okay. Simple. See at bus 1, you observe only one generator. You observe only one generator. There is no load. There is no load. But at this generator, what they said is real power generated by generator and reactive power generated by generator are given. Means PG and QG are known for you. PD, QD will be 0. PD, QD, because we don't have load there. PD, QD will be 0. Then obviously, what the net real power injection? 1 per unit. What the net reactive power injection? 0.5. Means at bus 1, you know both real and reactive powers. At bus 1, you know both real and reactive powers. What the bus 1 type? PQ bus we should answer. Okay, I'll write it. Just follow this thing. Follow this thing. Bus 1 I am considering first. PG 1, I'll say generator, real power PG1, 1 per unit. QG1, 0.5 per unit. But you don't have load there. I am keeping PD1 0, QD1 0. Why in the sense? I don't observe any load at that point. At that bus, I don't observe any load. That's why I'm keeping these numbers 0. What's the net real power injection? P1 is nothing but Pg1 minus PD1 value, which is 1 minus 0. Net reactive power injection is Qg1 minus Qd1, and this is 0.5 minus 0, 0.5. So, both real and reactive for set bus. So, bus 1 is going to be called as PQ bus. Bus 1 is going to be called as PQ bus. PQ bus. What's the bus 2 type? What's the bus 2? Just observe now. At bus 2, what they have given? PD, 1 per unit. Do you have any generator at this bus? Do you have any generator physically? No. No generator means PG is 0. QG also 0. PG 0, QG also 0. PD. Mod V also known here. Mod V is also given. Let's move. Bus 2. Bus 2. PD, it is 1 per unit, but you don't know about QD. You don't know about the value of QD. But one thing is sure that no generator means PG is equals to 0. No generator means PG is equals to 0. From these two, you can say net P2 is nothing but PG minus PD. So it will come to be minus 1 per unit. PG minus PD, that will come to be minus 1 per unit. Already voltage magnitude mod V2 1.05. 1.05. So as you know, both real power and voltage magnitudes, this bus is going to be called as PV bus. This bus is going to be called as PV bus. Bus 2 is a PV bus. Okay, next. Bus 3. Bus 3. Think about this one. Bus 3. PD QD. PD QD. But you don't know PG QG. Generator is there. But he didn't mention about the values of PG and QG. Even though PD QD, PG minus PD, generation minus demand is unknown. Reactive power, generation minus demand also unknown. So both P and Q values we don't know. But voltage magnitude and angle. Voltage magnitude and angle is known at the bus 3. Means what type of bus is that? What type of bus is that? Tell me please. Bus number 3. PG, QG are unknown. PG and QG are unknown values. That implies P3, Q3 unknown. P3 and Q3 are unknown values. P3 and Q3 are unknown values. Right? And mod V3 value, he has given that number 1.1 per unit. Delta 3 is equals to 0 degree. Yes. Okay. That implies bus 3 is a slack bus. Bus 3 is a slack bus, we should say. Bus 3, it's a slack bus. Okay, bus number 4, you tell me. Bus number 4. We know PD, QD here. We know PD, QD. But you don't have generator. So obviously PG, QG will be 0 at this bus. So PG minus PD, QG minus QD. So we know both P4 and Q4 values. So bus 4 is a PQ bus. Bus 4 is a PQ bus. Bus number 4. Right? If you want no generator. No generator. So PG is equal to 0 and QG is also equal to 0. Load is at that bus. PD number, how much? How much is the load? 1. QD is 0.2. QD number is 0.2. So P4, PG minus PD minus 1. Q4, QG minus QD. So it is minus 0.2. So this bus is going to be called as PQ bus. That bus is going to be called as PQ bus. Yeah. So by this problem, I want to give one more conclusion to you regarding bus classification. Just observe now. Yeah, correct. Just listen. Bus 2, you look first. Bus 2. It is looking like a load to you. Yes or no? Bus 2 is looking like a load. but still we are calling this as a PV bus, right? Rather than calling this as a load bus, we are calling this as generator bus, or you say PV bus. Why? Why in the sense? Because he mentioned the values of real and real power and the voltage magnitude at this bus. Please listen to my words, please. At the bus 2, it's a load, surely it's a load, but still we are calling this as a PV bus, so-called generator bus. Why it is so means, according to the values of the real power and the voltage magnitudes mentioned. For example, you see bus 1. Bus 1 you see once. Bus 1. PG, QG are given and you don't have a load, right? Even though you are observing physically a generator there, as you know, real and reactive force here, we are going to call that bus 1 as PQ bus, or you can say that as a load bus. See, the preference for what we have to give to decide whether the bus is a PV bus or PQ bus or slack bus is the data. Whatever the numbers they will provide, which values they are providing at that bus, whether they are providing real power, reactive power, voltage magnitude, delta, based on these 4 quantities, what they will mention at that bus, we should decide, is it a load bus or generator bus or slack bus, theoretically, while you are doing the load flow analysis. I think I discussed the 2 varieties here. First variety, what I said is, first variety means previous problem, what I said is, without discussing about what the known quantities and what the unknown quantities, just I said the bus names, right? And I asked you to get which are the PQ buses numbers and which are the PV buses numbers. That's one way of asking the problem. Other way of asking the problem is by giving the data directly. By giving the data, we should follow the data only. We don't need to think about what element we have at the bus. We should follow the data. If we didn't get the data, then we should have to follow what the element they have kept at the bus. Yeah, all of you have understood this one. Please tell me. Kindly tell me. Have you understood this 2 varieties? For what we should give the preference now? Is it to the element what we keep at the bus or known values? For what we should give the preference? Yeah. According to the values, whatever they have mentioned. According to the values, whatever they have mentioned, that we should prefer always to decide whether the bus is a PV bus or PQ bus. Okay, third verse, somebody is asking me, third verse, kindly observe here, third verse, bus 3. You know voltage magnitude already. Delta also given for you. Okay, so V and delta are known. Let's think about P and Q. Generator mentioned at this bus, but you don't know real power generated by generator. Generator shown at the bus 3, but you don't know about the real power generated by generator. And you don't know about the reactive power generated by generator also. But you know load, okay, load. What is PG minus PD? PG is unknown, nah? PG is unknown, right? So obviously real power at the bus 3 is unknown. Reactive power. QG minus QD. QG is unknown. So obviously Q also unknown at the bus 3. So at the bus 3, I don't know the real and reactive powers, but I know the voltage magnitude at the angle. So that bus 3 is going to be treated as a slack bus. Bus 3 will be treated as slack bus. Net P and Q. Else you say at bus 3 you have written PG and QG are unknown values. So what is P3 actually? PG3 minus PD3, right? As PG is unknown, P3 is unknown for you. What is Q3? QG3 minus QD3. So QG is unknown, so obviously Q3 is also unknown. Slack bus we discussed long back. Sir, PV, PQ is also bus classification. So we have 6 types of buses. See, Sai Charan Reddy, mathematically speaking, we have only 3 buses here. Slack bus, PV bus, PQ bus. That's it. PV bus can also be called as either generator bus or voltage control bus. PV bus can also be called as either generator bus or voltage control bus. PQ bus can be called as simply load bus. Okay, irrespective of element, whatever you keep at that bus, according to the values, whatever they mention, based on that we decide. Is it a PV or PQ? Okay. We don't have 6 types of buses. But there is a load. Okay, load is there. What we do with that, Sivanath? We know PD and QD, that's okay. but you don't know net real power and net reactive power, right? You know load, okay. Then what do you do with that? Because as you don't know about the generator, real and reactive power supply, obviously, even though you know the load, I should not say net real power and net reactive power as known values, right? Okay, done. Fine. So this is about bus classification we discussed till now. See, whatever the load flow equations we have now, these are non-linear algebraic equations as we have mentioned. Non-linear algebraic equations. But to solve these equations, a single step solution can't be achieved. We can't get a single step solution for this one. These equations, load flow equations, we are going to solve by means of iterative methods. Okay. So I'm going to take up the heading as iterative methods. To solve load flow equations. Iterative methods to solve the load flow equations. Yeah, so I'm listing out the methods. Kindly go through it. First one, it's a Gauss method. Okay. Second one, Gauss-Seidel method. Else you can say GS method shortly. GS. Third one is a Newton-Raphson method. Call it as NR method, you can say shortly. And fourth one is a decoupled load flow. Load flow method, right? DLF method, you can say. And fifth one is a fast decoupled load flow method, FDLF. Fast decoupled load flow method. We are naming this as FDLF method. Yeah, so these are the various methods we have. Gauss-Seidel, these two are one way actually. These two are one way of solving the equations. NR, DLF, FDLF, these three will fall in some other category. Okay, Gauss and Gauss-Seidel is in one category. NR method, DLF method, FDLF method, these three are in other category. Okay, so let's start with the first one, Gauss method. Simple one. First method. Gauss method. Yeah. Gauss method. Look here. So complex power injected into the ith bus. That equation I'm writing. Complex power injected into the ith bus. Injected into ith bus. SI. It is generally written as VI into II conjugate. Will be generally written as voltage VI and current is II. So VI into II conjugate, we can say. VI into II conjugate. And I'm making this change. Apply conjugate on both sides. Okay. Apply conjugate on both sides. Apply conjugate on both sides. Yeah, this we are doing only for the simplification. It's not necessary. Strictly speaking, it's not necessary. We are doing this one only for simplification purpose. So I can write SI conjugate here is equal to VI conjugate into II. Generally, you know, net complex power inject into ith bus as PI plus JQI. PI plus JQI. Net complex power inject is SI equals to PI plus JQI. Okay, next thing. What is the current equation from this now? II equals to SI conjugate by VI conjugate. What do you mean by SI conjugate here? SI is something like PI plus JQI. After applying conjugate, you get PI minus JQI. After applying conjugate, you get PI minus JQI. I will write it later. First of all, What is the equation for the current injection II? What is the equation for the current injection II? Already we have discussed in the earlier classes. Just I am going back and I will show you that. Just look this one. II equation we have written from the Y bus. II equation we have written from the Y bus. Yi1 V1 plus Yi2 V2 plus and so on up to Yin Vn. Okay, that equation we are repeating now. Ith bus current injection from the Y bus matrix. From the definition of Y bus matrix. Definition of Y bus matrix. Ith bus current injection we can write as Yi1 V1 plus Yi2 V2 plus Yi3 V3 plus and so on Yii Vi plus and so on Yin Vn. Like this you can say ith bus current injection equation Yi1 V1 plus Yi2 V2 plus and so on up to Yii Vi plus and so on up to Yin Vn. Okay. See, actually we have n terms here, right? N terms here. In these n terms, we'll take one term out. So called ith term we'll take out. Remaining n minus 1 terms we'll write in a sigma. Remaining n minus 1 terms we'll write in a sigma. Kindly observe. Yii Vi plus this one. This one I have taken out. Remaining terms I will be writing in sigma. Sigma j equals to 1 to n Yij Vj. J is a letter variable. J is a letter variable. Sigma j equals to 1 to n Yij Vj. But the j should not be equals to I. J should not be equals to I. Okay, because that ith term we have taken out already. Yia into Vi we have taken. That's why we should keep here j not equals to I. This is the ith bus current injection. Simply, you substitute this ith bus current injection in this equation. Si conjugate by Vi conjugate. Right. Therefore, Yii Vi plus sigma j equals to 1 to n, j not equals to I, Yij Vj is equal to Si conjugate by Vi conjugate. Si conjugate by Vi conjugate. Okay, this sigma, whatever you have, that you take to the other side. Sigma you take to the other side. Yeah, please complete it. I will move to next slide. Okay. So Yii Vi is equal to Si conjugate means I will write Pi minus JQi. Denominator you have Vi conjugate minus sigma j equals to 1 to n Yij Vj, and this j is not equals to I. Like this we get. Just if you are transferring this sigma to the other side. Si conjugate means Pi minus JQi. Pi minus JQi. Like this you get. And what the ith bus voltage Vi now? Ith bus voltage equation will be 1 by Yii into 1 by Yii into this whole Pi minus JQi minus sigma j equals to 1 to n Yij Vj, j not equals to I. J not equals to I. Here, it's the ith bus voltage we have derived. Ith bus voltage we have derived. See, one very simple thing I will tell you. Just listen. One very simple thing. For example, after doing load flow analysis, or without doing load flow or anything, in a simple way, you know voltage magnitude as well as the angle at all the buses in the system existing. At all the buses in the system, you know the voltage magnitude value as well as you know the angle value also. You know voltage magnitude value as well as you know the angle value also. Can I say almost we have completed the load flow analysis? You know the voltages at all the buses existing in the system. Magnitude as well as the angle, you know, at all the buses. Can I say that? Load flow is almost over. Yes or no? Yeah. Because see, once after knowing voltages at all the buses, listen please, listen please. Once after knowing the voltages at all the buses in the system, after all, what we should do further? We have to calculate current flows in the system, and we have to calculate the complex powers, and we have to know what is the real power and the reactive power. That's it, right? It's a simple thing. Almost we reach to the end of the load flow, right? After knowing voltage at all the buses. Likita, are you understanding this? Tell me, please. So the basic aim of the load flow analysis right now, is to find out the voltages at all the buses existing in the system. To find out the voltages at all the buses existing in the system. That's what our aim now. So in that perspective, I am attempting to get the ith bus voltage by using this equation. Okay, listen please, listen. Little confusions, but still you should understand in this way. Ith bus voltage I have to calculate by using this equation. That is equal to 1 by YII. YII value we know from Y bus. YII we know from Y bus. What about PI and QI? PI and QI. These two values might be known. Assume that it is a PQ bus. Assume that this bus is a PQ bus. So I know the values of PI and QI. And again in the denominator we are getting VI, right? See the thing here. To calculate the ith bus voltage, we need again ith bus voltage here. VI is coming again as a function of VI. That's a problem. So in this case, what we'll assume is we'll take that ith bus voltage VI as something like 1 at an angle 0 degree. Listen, don't write, just listen. Ith bus voltage I will be substituting as 1 at an angle 0 degree. I will exercise this equation. I'll calculate the ith bus voltage now. We'll get a new value. For VI. That new value we substitute back into the equation. Again, I will calculate the voltage VI by using the equation. We'll get a new value of VI. That value we resubstitute back into this one. Again, we'll get a new value of VI. Again, resubstitute back, get a new value of VI. Resubstitute back, get a new value of VI. Understood this procedure? I need your response now. Have you understood the procedure? What I said now? Yeah. First, we have taken some value of VI, like 1 at an angle 0 degree we have taken, right? After putting this 1 at an angle 0 degree, I will calculate this equation. I will get some new value of VI. That value we substitute back here. We'll get new value of VI. That value we substitute back here. We'll get new value of VI. Substitute back here. Get a new value of VI. How far we have to repeat this one? Tell me please. How far we have to repeat this one? Up to the point wherever we don't get any change in the value of VI. Till the point where the same result is going to be repeated. Up to that point, we should do this study. Following all of you, the point where we get equal voltages from previous calculation to the present calculation. If we don't get any change in the value, that point we say we are meeting the convergence. Following all of you, right? Yeah. So I can say from this point now. See, putting some value of VI and getting some new value, resubstituting back. This we are going to call iterations. Let us say, what is the ith bus voltage? Ith bus voltage in the k plus 1 iteration. Ith bus voltage in the k plus 1 iteration. Let's write here. Ith bus voltage in k plus 1 iteration. In k plus 1 iteration. Ith bus voltage in the k plus 1 iteration. So I can say it is VI k plus 1 here. VI k plus 1 is equal to, just follow the thing, 1 by YII. I'll keep the same equation what we have, this one. I'll keep the necessary changes. Just observe here. 1 by YII Pi minus jqi by Vi. Vi in which iteration we should take here? Ith bus voltage in which iteration we should take? Previous iteration, so called kth iteration. So Vi k conjugate. It is a kth iteration value. Kth iteration value minus sigma j equals to 1 to n, j not equals to I, Yij Vj. Here also we have some voltage term, right? Here also we have some voltage term. What are these voltages we should consider now? Kth iteration voltage so D. So called previous iteration voltages we have to consider. We should consider the previous iteration voltages. Previous iteration voltages. Kth iteration voltage. Fine. So this is the ith bus voltage in the k plus 1 iteration. 1 by Yii into Pi minus jqi by Vik whole conjugate minus sigma this voltage. Following? But whatever the things we have discussed just now, that I want to recall. When we are going to get the convergence. That's one point we have to discuss. First point, convergence criteria. Convergence criteria. Just listen. Convergence criteria I am taking up. Just listen here. Actually, we should find out the difference between the voltages. Listen, all of you, stop writing, just listen. Difference between the voltages we have to calculate. That difference is nothing but k plus 1 iteration ith bus voltage to kth iteration ith bus voltage. I will find out the difference. Vik plus 1 minus Vik I will find out. But I want to take up only magnitude of this. Magnitude of Vik plus 1 minus Vik. Okay. Tell me, very simple question. How many this type of numbers you get now? It's called generally as error. Vik plus 1 minus Vik is going to be called as error. How many this type of errors we are going to get? Anybody please tell me. We completed the k plus 1 iteration, you assume. How many this type of errors we are going to get? N buses? N. Because if you keep bus 1, you keep one number. Bus 2, you get one number. Bus 3, you get one number. So at each bus, you are capable to find out the error, right? Yeah. Please tell me. Are you understanding this? Error in the ith bus voltage. Okay. Similar to that ith bus, we have the error at remaining all buses also, right? Like that, how many we have these error magnitudes means n errors we have, n values we have. In those n values, whatever is existing, n numbers, pick up the highest value. Maximum value you pick up. From this. Pick up the highest value, maximum value. If that maximum value, what we are saying now, what you pick up now, less than some epsilon. Epsilon is going to be called as tolerance for convergence. I'll write here. Epsilon is going to be called as tolerance for convergence. Generally, it's a very, very low value. The people will treat this one 0.001. How much value we have to take for epsilon means that depends upon your accuracy required. I am repeating back. Maximum of these n numbers what we have, if it is less than 0.001. See, maximum value what we have itself is less than 0.001 means remaining all numbers will be less than 0.001. So if this is happening, then I can say we reached the convergence. Right? So then if maximum of this value is less than epsilon, then convergence was achieved. By calculating this iteration values, what we know, sir? Ultimately, Vaishnavi, our aim is to calculate the voltages, right? In the load flow analysis. After getting voltages, we are capable to know what's the value of real and reactive powers. By doing these iterations, we are capable to find out what are the voltages at various buses in the system. That's it. Yeah. Okay. So this is about the convergence criteria. Convergence criteria. Next thing. See, generally, I said in the previous case, let us say first iteration you want. First iteration. Listen, please. Listen, all of you. Listen. First iteration. K that will be number of iterations only. K in the sense number of iterations, how many you are doing. But sir, in each iteration, error will be reduced. Okay. Each iteration we have to do this one. For every iteration, at the end of the iteration, we have to calculate this error value. And we have to calculate error at all buses at each iteration. For example, first iteration we completed. We calculate error at n buses. Take up the maximum value. Check. Is it less than epsilon or not? If it is not, go for next iteration, second iteration. Complete the second iteration. Calculate the errors. Take up the maximum value. If it is it less than epsilon or not? Check. If it is not, go for the next iteration. Up to the point wherever we are going to get, up to the iteration number wherever we are going to get, this error magnitude is coming less than epsilon. Up to that point, we have to do the calculations. Because all buses should settle down to close values, right? Why we have to compare all buses errors means all buses should settle down to close values. Does voltage at Vn plus 1 bus exist physically? No. There is no Vn plus 1. Where we have Vn plus 1, Ankur? We don't have Vn plus 1, right? Only Vn we have. Vn. That's it. Okay, let's continue. See, while we are starting the first iteration, listen to me. While we are starting the, how we get the kth iteration value Vj. Yeah, anonymous attendee, while we are doing k plus 1 iteration, already you have done the kth iteration, right? Already we have done the kth iteration. So by that way, you will get it. For example, if you want to write the iteration 1, for example, here, iteration 1. So I will copy the same equation here. This equation only I am going to copy. Look here. Iteration 1 I am keeping. Means in place of k plus 1, you keep 1 here. Means k is equals to 0. K is equals to 0. So here you get 0. Here also you get 0. 0. VA 0. Here also you will get 0. Like this you will get. First iteration, ith bus voltage we want to do. Okay? Just listen. What is VA 0? We don't know. Because we have not done any calculation, right? We have not done any calculation. This is the first calculation we are making. And we don't know the value of VA 0. If we don't know that, we have to assume that number somewhere. Okay. How much in the sense, we are going to assume that voltage magnitude 1 per unit, angle 0 degree. Okay. That's what we are going to name it as flat start. Means before starting the first iteration, wherever you don't know voltage magnitude, you assume that voltage magnitude as 1 per unit. Wherever you don't know the angle value, you assume that as 0 degree. All of you getting my words? Getting the meaning of flat start? Yeah. So I'm writing now flat start is the next point in this discussion. Flat start, which is valid for all other remaining load flow methods, which we are going to continue. Flat start. So you're right. Before starting first iteration, iteration 1, assume mod V equals to 1 per unit. At what buses you know mod V? At what buses you don't know mod V? Tell me please. Magnitude of voltage at what buses you don't know? At only PQ buses, right? PV bus, you know mod V. Slack bus also, you know mod V. At only PQ buses, you don't know mod V. Means we have to take this flat start voltage magnitude as 1 per unit only at the PQ buses. Only at the PQ buses. Why can't we take at PV? Why can't we take at slack? Means because that mod V value already given in the data at those particular buses. Okay, assume mod V equals to 1 per unit at PQ buses and delta equals to 0 degree. At what buses you should assume? Delta equals to 0 degree. At what buses you should assume? Tell me please. At what buses you don't know angle delta? At what buses you don't know angle delta? So you know the angle only at the slack bus. You know the angle only at the slack bus. You don't know angle at the PV bus and you don't know angle at the PQ bus. Following all of you. So at all buses except slack, we should assume that delta equals to 0 degree. At PV and PQ buses, you write. PV and PQ buses except slack bus. In bracket. Except slack bus. At all other remaining buses, we should assume that delta is equals to 0 degree. This is the meaning of the flat start. In the man graph, just as a conclusion, as I said you earlier, before starting the first iteration, wherever you don't know the voltage magnitude, you assume that as 1 per unit. Wherever you don't know the angle, you assume that as 0 degree. So by this way, we are going to get the initial states of the system. Initial states of the system. These initial states, we are going to substitute in this equation. By that way, we get the iteration 1 result. That iteration 1 result, we will use for iteration 2. We'll use for iteration 2. Whatever the iteration 2 result, that will use for iteration 3. Like that, we have to repeat up to the point of time wherever we are going to get the convergence. Okay? 2 points we discussed it now. First point is convergence criteria. Second point is a flat start. We have one more point, few more points to discuss, particularly with respect to PV bus. Particularly with respect to PV bus. I will show in the next slide. Next slide. If PV bus exists in the system, I'll say. PV buses exist in the system. PV buses exist in the system. Just listen to this one. I'll start directly with an example. Just listen to me. I'll start directly with an example. For example, bus 1 is a slack. Bus 1 is a slack. Bus 2 is a PV, and so on. We have some number of buses we have. I'm treating only bus 1 and bus 2. Remaining buses are there. Bus 3, bus 4, bus 5, bus 6, and so on up to here. But here what I'm saying is bus 2 is a PV bus. Bus 1 is a slack bus. Bus 1 is a slack bus. Stop writing. Stop writing. Just listen. Just listen. Iteration 1. Bus 2 voltage. Iteration number 1. Bus 2 voltage. Iteration number 1. Bus 2 voltage. Just observe. V21. Iteration number 1. Bus 2 voltage. V21. V21. I'm writing formula. Just go through it. Same formula. What we have written earlier, that I am repeating now. 1 by Y22. Y22. Into P2 minus JQ2 by V20 conjugate. V20 conjugate minus sigma J equals to 1 to N. It's the second bus we are taking up, right? J not equals to I means 2 Yij Pj K. K in the sense 0. Like this we should say. All of you understood this equation? Please tell me. Have you understood this equation, what you have written? Second bus voltage in the first iteration. equal to 1 by y22 into P2 minus JQ2 by V2 0. Previous iteration is 0. Conjugate minus sigma J equals to 1 to n, J not equals to Yij Bjk. Bjk means previous iteration Bj 0. Bj 0. Okay. Next, listen now. Listen. See, y22 value do you know or not? From y bus. From y bus, definitely I know the value of y22. I know it. What about P2? What about P2 value? Do you know it or not? P2. Yes. P2 also I know because it is a PQ bus. So definitely Y2J. Y2J. This is Yij. Instead of I, we should keep I. I is nothing but 2 here. I is nothing but 2. Okay, listen. P2 do you know? Yes, it's a PV bus. Do you know Q2? Do you know Q2? Yes or no? Do you know Q2 value? We don't know, right? Because as a bus is a PV bus, we don't know the value of Q2. But without that Q2 value, we can't solve this equation. Without that Q2 value, we can't solve this equation. In that situation, what we have to do is, what we should say is, before starting the iteration at the PV bus, this Q2 value what we have, that we should calculate by using basic power flow equation. With the present voltages what we have. With those voltages and basic power flow equation, by using that, we should calculate the value of reactive power Q2 before starting this iteration. That's the first statement you have to remember in the PV buses. Okay. So first statement I am writing now. Just observe what I am saying you. Statement. At PV bus, before starting the iteration, it is necessary to calculate reactive power. It is necessary to calculate the reactive power by using present states, means present voltages you can write. If you are unable to get it, you write voltages and power flow equation. The present states and power flow equations, we should calculate the value of reactive power before starting the iteration at the PV bus. So I think all of you understood this one. Is this clear what I said? One more thing I want to discuss now. Second point. Listen now. Listen. Second point. See, we calculated the value of Q2 with the present state and equation, and we calculated this V2 also. We calculated the value of V2 also at the end of the first iteration. But you see, bus 2 is a PV bus, right? Bus 2 is a PV bus. PV bus means what? Mod V value they will give in the data already. But after calculating this one, there's a change in the magnitude as well as the angle also. Okay, so in that case, what we should do is, as a bus 2 is a PV bus, after doing calculation, whatever the mod V2 you get in the calculation, that we should avoid. That mod V2 value we should keep as it is given in the data. Only angle has to be updated. First, I will write this statement. I will show you with some numbers. Yeah, let's write like this. After doing voltage calculation, voltage calculation at PV bus. After doing voltage calculation at the PV bus, mod V value shall be discarded. Discarded means you should remove it. Okay. Discarded, and it shall be kept as given in data. Full stop. Only delta variation shall be considered. Only delta variation shall be considered. Okay. Only delta variation shall be considered. This point I am going to explain with some numbers. Please write it. Yeah. So let's move to the next slide. Just look here. For example, bus 2 is a PV bus. I am considering bus 2 is a PV bus. Whereas mod V2, magnitude of that voltage, 1.05 per unit, it is given in the data. In bracket, I'll write it is given in the data. Magnitude of voltage, mod V2 is 1.05 per unit. That's given in the data. Listen all of you. I'll try to show the things whatever I discussed till now. Just listen. Present state means present voltages. That's the meaning. I said already. Okay. See, while you are starting the first iteration, look. While you are starting the first iteration, as a bus 2 is a PV, already I know voltage magnitude. I have to assume angle now. How much? 0 degree. So flat start. Means I will be assuming delta 2 0 degree. After taking the delta 2 as 0 degree, what is bus 2 voltage in the initial state? In the initial start, what is the bus 2 voltage? Now, bus 2 voltage in the 0th iteration or starting will be 1.05 at an angle 0 degree. Is that okay? Tell me please. Is that okay? V2 0 is equals to 1.05 at an angle 0 degree. That's the initial start voltage at the bus 2. Now, we conducted the iteration 1 by using the equation what we studied. So, iteration 1 result I am writing now. Iteration number 1 result I am writing now. V21. Iteration 1 result is V21. V21 is equal to, I am writing the number. Just listen. We have done the calculation. And I am writing it. It is coming something like 1.12 angle of minus 3.6 degree. Like this I got. Calculation I have done. I got this value like 1.12 at an angle minus 3.6 degree. But listen all of you. But bus 2 is a PV bus. Already bus 2 voltage magnitude they have given in the data 1.05. But this is saying that magnitude is 1.12, which is wrong. Yes or no? So that whatever the magnitude we got now, that we should discard. That we have to remove completely from our view. After removing this number, we should replace this with 1.05 per unit. So I should say V2 at the end of the first iteration as 1.05. How is the angle? As it is, angle whatever you have calculated now minus 3.6 degree, that we should consider as an angle. Angle will be minus 3.6. So from this point onward, we should use the first iteration result as this only, rather than the above. So we should say 1.05 at an angle minus 3.6 degree. This we should use for the second iteration. Again, after doing second iteration, you may get a change in the magnitude that we have to remove. We should keep that voltage as it is 1.05 and angle variation, anything we got that we have to consider, and we should proceed further. So I think all of you understood this one. Please tell me. Yeah. Yeah, Manjunath, as a bus 2 voltage is a PV bus, voltage magnitude they have given in the data, right? As it is a known value, as it is a constant value. Bus 2 voltage magnitude as it is a constant value, which we should not allow to vary in the calculation. Which we should not allow to vary in the calculation. That's why any magnitude you got here, that we should remove and we should keep the magnitude as it is given in the data. That's the thing. Okay, done. So one more point you have to remember. That's second or third point, I can say. Third point. At the end of each and every iteration, means after calculating all the bus voltages after reaching to end, we should check Q limits at the PV buses. Generally, at the PV buses, there exists some Q limits, right? There exists some Q limits. So those Q limits. So it's not error anonymous certainty. Error is not angle actually. We are going to consider only angle change, you say. Don't say error. Don't say error. Error means that's a difference, right? Difference between previous iteration to the present iteration. Yeah, look here. So at the end of each iteration, Q limits has to be checked. At PV buses. This also you have to remember. Q limits has to be checked at the PV buses. If there is any violation in the limit, you take VIK plus 1 minus VIK, Bhaskar. Even though you don't have any magnitude change, there is an angle change, right? Because of angle change, definitely you have an error. Okay, done. So next thing. One of the main disadvantage of this method, particularly Gauss method, is it's going to take a huge number of iterations to give the solution or to meet the convergence. It's taking a large number of iterations. That's the main problem of this method actually. See, I will write the equations now. I'll write the equation. Just try to observe these equations once. Just look here. Equations I'm writing. Equations, bus voltage equations in iteration 1, I'll say. Bus voltage equations, writing it in iteration number 1. Assume that bus 1 is a slack. Remaining buses I'm writing. Remaining buses. Bus 2 voltage iteration 1. Just observe the formula. Kindly observe the formula. Yeah. V21. 1 by Y22. Just look here. P2 minus JQ2 by P2 0 conjugate. I'm going to tell some more thing to you. That's why I'm writing the equations here. Minus. Look here. It is sigma something. Sigma. Don't bother about that. Just I will write directly. Here, what you get is Y21 V1, Y22 V2, Y23 V3, Y24 V4, Y25 V5, and so on. Like that, you will get. Minus what you get is Y21 V1, Y22 V2, Y23 V3, Y24 V4, and so on. But in that summation, Y22 V2 already you have taken out. Y22 V2 you have taken already out. So remaining terms, what you get now? Y21 V1, Y23 V3, Y24 V4, minus and so on. Like this you can get. Minus and so on. But you see, whatever the V3 we have, that's the previous iteration. V4 also previous iteration. V1 is a slack bus voltage which is constant. V1, that's a slack bus voltage which is constant. Okay, next. Bus 3 voltage in the first iteration. Just observe. 1 by Y33 into P3 minus JQ3 by V30 conjugate minus Y31 V1. What you get now? Y32 V2, Y34 V4, Y33 V3 already we have taken out, minus Y35 V5, minus and so on. Like this, you'll get that bus 3 first iteration. And whatever the V2 we have, that's the previous iteration result. V4, previous iteration. V5, previous iteration. Next, bus 4 voltage. 1 by Y44 into P4 minus J Q4 by V40 conjugate minus Y41 V1, Y42 V2, Y43 V3, Y44 V4 already we have taken out, and you get Y45 V5. So on. And these are the 0th iteration voltages we should keep: V20, V30, V50, and so on. See, these are the set of equations what we are solving. These are the set of equations what we are solving. Yeah, just listen, just listen. In the Gauss method, See, one simple observation is here. One simple observation. Just look here, just look here. See, while we are calculating the fourth bus voltage, in the first iteration, definitely before this, you have updated the second and third buses. You have updated the second and third buses voltages in the first iteration. But again, to calculate that fourth bus voltage in the first iteration, why you are using 0th iteration voltages for bus 2 and bus 3? Why you are using 0th iteration voltages for the bus 2 and bus 3? You keep these voltages as the recently updated values. Just now we updated the bus 2 voltage in first iteration, that you substitute here. Just now we updated the third bus voltage in the first iteration, that you substitute here. Remaining buses 5, 6, 7, you have not updated, you take it as a previous iteration voltage only. All of you getting my words? For example, you are doing bus 3 voltage calculation. See, while you are doing bus 3 voltage calculation, before that, you have updated the bus 2 voltage. You have already updated the bus 2 voltage. So rather than taking V20, you consider this as V21. Remaining buses 4, 5, 6, 7, you take it as 0th iteration voltage. Take it as 0th iteration voltage only. Okay. After making this small modification, that method is going to be called as Gauss-Seidel method. Gauss-Seidel method. Okay. All of you getting this? Please tell me. Getting some idea about this method? Second method, what I am saying now? Simple. There is very simple comment. What we should say for the next method is, whatever the recently updated voltages you have, that you use in the iteration. That's it. Okay. For example, if you are calculating 10th bus voltage in the first iteration, already up to 9 buses you updated in the 10th first iteration. Those voltages you use. Remaining buses you have not updated. Those voltages you take it as previous iteration voltage one. Yeah. So let me write the next heading. That is a Gauss-Seidel method. Gauss-Seidel method. Gauss-Seidel method. GS method we can say. GS method. Always use recently updated voltages in the calculations. Use recently updated voltages in the calculations. The calculation, we should use a recently updated voltages. Iterations will reduce little bit. The number of iterations will be reduced definitely by using Gauss-Seidel. So, for example, to calculate Look here, calculate ith bus voltage in k plus 1 iteration. K plus 1 iteration. Ith bus voltage in the k plus 1 iteration. What voltage you should use? What voltage you should use? 1, 2, and so on up to I minus 1. 1, 2, and so on up to I minus 1 buses. Already updated in the k plus 1. Na? So buses, k plus 1 iteration voltage. K plus 1 iteration voltages. And remaining buses are what? I plus 1, I plus 2, and so on up to n. And so on up to n buses. Which iteration? Kth iteration voltages. Kth iteration voltages shall be used. Voltages shall be used. 1, 2, and so on up to I minus 1, k plus 1 iteration voltages. Remaining buses, we should use a kth iteration voltage only. Equation will not change. Equation will be as it is. Whatever the equation we have taken earlier, same equation will repeat, but you have to modify that iteration numbers for the voltages. That's it. So I'll write now. I'll write in the next slide. Yeah. So observe. It is ith bus voltage in the k plus 1 iteration. Ith bus voltage in the k plus 1 iteration equals to 1 by YII into PI minus JQI by VIK conjugate. It's the kth iteration value on previous. But here minus sigma J equal to 1 to I minus 1. We should use a k plus 1 iteration because just now we have updated it. And remaining, I'll say minus sigma J equal to, I'll start from I plus 1 to n Yij Vj. This will be the kth iteration. That will be the kth iteration. That will be the kth iteration. So J not equals to I satisfied it. J not equals to I was already satisfied because I have taken J value 1 to I minus 1, first range. Second range, I plus 1 to n means J equals to I was removed. J equals to I was removed. So this will be the ith bus voltage in k plus 1 iteration by using the Gauss-Seidel method. See, definitely by moving from Gauss method to Gauss-Seidel, definitely number of iterations are going to be reduced. But that number of iterations reduction may not be huge. For example, if you have a 100 bus system, let us say 100 bus system, Gauss method is giving the convergence. Let's say for 500 iterations. It's taking 500 iterations to give the convergence. 500 iterations it is taking to give the convergence if the 100 bus system, Gauss method. Similarly, if you think about the Gauss-Seidel method, so-called the modified one, it may be taking the number of iterations, let's say 470. Number of iterations definitely reduced, but one thing what you have to understand is the variation is very less. Maybe it's going to be reduced by 30 or 20 or maximum 50. Okay, number of iterations will decrease definitely, but that reduction, right? But that reduction may not be very, very high. That reduction in the number of iterations may not be very, very high. Okay. And in order to make up that number of iterations further low, or you can say in order to accelerate the convergence, the people introduced one more method called as Gauss-Seidel method with the acceleration factor. GS method with the acceleration factor. That I will write. What we do in that I will tell you. Okay. So GS method with the acceleration factor. GS method with the acceleration factor. I'll call this as alpha. Calling this as alpha. GS method with the acceleration factor, I'm calling that as alpha. Listen, please, listen. Actually, look all of you. Actually, by this GS method, one of the observation made by the people is, one simple observation made by the people is, for example, if the voltage value starts decreasing as we are doing iterations, if the voltage value starts decreasing, that will continue to decrease iteration by iteration. It will continue to decrease and it will settle down to some value. That's the thing what it will do. Similarly, in case of Gauss-Seidel method result, if the value starts increasing iteration by iteration, it will start increasing continuously and finally it will settle down to some value. Following the means we do have a sort of linear variation. In the value of voltage iteration by iteration. That's the observation what we have to make. That linear variation what you are getting now from one iteration to other iteration, that variation we are going to accelerate. Or the change whatever you get, that we make high. By that way, we are going to get the result a bit quickly by decreasing the number of iterations. Okay, just I will write that one. Please look here. GS method gives voltage values as a linear variation during iterations. Okay, so to get a quick convergence, the variation, or you can say error, will be accelerated by using alpha. So called acceleration factor alpha. All of you getting it? GS method gives voltage values as a linear variation during iterations. To get quick convergence, the variation or error will be accelerated by using alpha. Now, simple, very simple. I am writing in the next slide. Kindly go through it. Next slide. What is error here? What is that error? Error is nothing but VIK plus 1 minus VIK. This is an error, right? I need your response, please. Is it the error? VIK plus 1 minus VIK. That's a variation. What you got from present iteration to the previous. How much change you got? This change we should multiply with alpha. That change we should multiply with alpha. After multiplying that, you make the change larger. This we should add to previous iteration result, value, and this is the resultant voltage in the K plus 1 iteration, accelerated value. Resultant ith bus voltage in the K plus 1 iteration, right? In the K plus 1 iteration, accelerated value equals to VIK plus error into alpha. error into alpha. Generally, this alpha, for example, I'll tell you one simple question. If alpha is equals to 1, what you should say? If alpha equals to 1, what you should say? Alpha is 1. So VIK will be cancelled out. VIK plus 1 accelerated value and VIK plus 1 calculated value both are equal. VIK plus 1 accelerated and VIK plus 1 calculated value both are equal. Means what you should say? There is no acceleration. There is no acceleration. No acceleration. No acceleration. Yeah, main advantage is simply reducing number of iterations. That's it. Bhaskar, main advantage is reducing the number of iterations. Getting a quick convergence is nothing but reducing number of iterations. And for example, if alpha is greater than 1, then only we can say there is an acceleration to the convergence. There is an acceleration for convergence. There is an acceleration for the convergence. Okay. But greater than 1 in the sense, we can't use any number as you wish. Greater than 1 in the sense, you can't use any number as you wish. Generally, there is a prescribed limit for this alpha, right? Optimum value of alpha. That will be in the range of 1.2 to 1.6. Generally, we use to keep the alpha in this particular range. Then only we are going to expect number of iterations reduction as well as we have a quick convergence. So you can say number of iterations reduced by using alpha. But again, that reduction may not be very, very high. Again, that reduction may not be very, very high. Because in the earlier case, I said by using Gauss method, we are getting 500 iterations. Just I will show that slide. Gauss method is giving the convergence for 500 iterations. Gauss Seidel is taking 470. For example, GS method with acceleration may take 450, 450 or 440 iterations it may take. Say number of iterations will decrease definitely by using Gauss Seidel method with acceleration. Most of the times. Sometimes the people will say, even though you use alpha, number of iterations may increase also. It may fire out sometimes. Because it's not a definite mathematical thing. There is some sort of ambiguity in that alpha multiplication, taking care of that addition and all. Okay. So taking this alpha in an optimistic way, will decrease the number of iterations, but that reduction may not be a high value. That's the problem. Okay. See, one thing what you have to understand is, in all the things whatever we have discussed till now, Gauss Seidel with acceleration, we have not changed the method, right? We modified the method, that's it. We have not changed the mathematical method completely, so that you don't expect a great reduction in the number of iterations in this type of calculations. Okay, so this is the end of the Gauss and Gauss Seidel methods. Okay, so in the view of examination, they may not ask a problem for you, numerical problem. They may ask some theory question with respect to equations, alpha and all. Just go through that. That will be sufficient. Okay, so have a break for 15 minutes. After break, we'll start the Newton-Raphson method. So I'm giving 15 minutes break. So after break, I will be going with the Newton-Raphson method to do the load flow analysis. Yeah. So I've resumed audio, video, and screen. Okay. So the next method, what we are going to discuss is Newton-Raphson method. What we said earlier, Newton-Raphson method. Next reading. Newton-Raphson method. Okay. See, actually, the previous methods, what we have discussed earlier, Gauss method or Gauss-Seidel method. Okay, I'll write in the previous slide. Just look here. Look here. Gauss and Gauss-Seidel methods, what we discussed till now. Gauss and GS methods. These are used to solve. These are used to solve linear algebraic equations as well as non-linear also sometimes. Okay, used to solve linear or non-linear algebraic equations of real valued or complex value, anything. Okay, so used to solve. Used to solve linear or non-linear algebraic equations. Non-linear algebraic equations of real value or complex value or complex value. Used to solve linear or non-linear algebraic equations of real valued or you can say complex value. But you see this NR method, what I'm going to discuss now, this is used to solve only non-linear algebraic equations. Non-linear algebraic equations are real valued only. Okay, so this is used to solve only non-linear algebraic equations. Non-linear algebraic equations of real value. Non-linear algebraic equations of real value. Okay, done. Next, one more thing. See, actually, this NR method is going to be called sometimes as gradient method. Gradient method in the sense we'll be dealing with slopes, variation in the function or equation with respect to state, right? Those variations we are going to count. Based on that, we are going to do the iterations actually, right? So it's a gradient method. NR method is a gradient method. Gradient method. So which will be dealing with slopes. Dealing with slopes. Gradient, you can say dealing with slopes. Done. Next. Next I can say basic mathematical method here. NR method, basic mathematical method. I'll say NR method with one state first, with only one variable. Next, I will say NR method with two variables, two states. After doing these two, we will try to generalize the NR method and we will try to apply this one for our load flow problem. For our load flow problem. Okay? Yeah. So let's move ahead. Just look here in the next slide. Next slide. NR method with one state, I am saying. NR method with one state variable. One state variable. NR method with one state variable. Let's see. Let we have a non-linear algebraic function as f of x. Non-linear algebraic function. It is f of x, which will be equals to capital F. Okay, non-linear algebraic function f of x equals to capital F. For your understanding, I will write that function f of x something like x cos x plus x square is equals to 4, something like this. X cos x plus x square is equals to 4. And this x cos x plus x square, what we have here is f of x. F of x. And the number 4, what we have here is a capital. Number 4, what we have here is capital F. Now I want to tell you, this capital F, what we have here is a number. Capital F, whatever we have here, it's a number. That's what the interest I want to tell you. F of x is a function, capital F is a value, number. Okay, now listen. First, in order to solve this nonlinear algebraic function, we will take one initial start, something like x naught, some value. We'll assume that x value equals to some number x naught. Okay, so initial start is equal to x naught. See, after taking that initial start value x naught, you calculate this f of x naught number. Calculate the f of x naught value. Okay, so after calculating that f of x naught value, check whether this f of x naught is equal to capital F or not equals to capital F. That you have to check. See, for example, if that f of x naught value what we calculated is equal to capital F, if that f of x naught value is equal to capital F, then what I can say? Then x naught itself is a solution for the state. X naught itself is a solution for the state. X naught is a solution for state. Solution for the state. State means x here. State means x, variable. Okay, generally most of the times f of x naught value will not be equals to capital F. It won't be equal only. So in the next statement, what I can say is, if that f of x naught value is not equals to capital F, then what we should do? Then we will be adding some correction. We'll be adding some correction delta x to the value x naught. Add correction delta x to x naught such that f of x naught plus delta x value is equal to capital F, such that f of x naught plus delta x value is equal to capital F. Okay, now listen. Do you know the value of x naught? Yes, that's what we have taken earlier. Maybe some number 1, 2, 3, whatever the number you take at the initial state, that's the x naught. Capital F is a known value from the function. Delta x is a unknown value. Means what you have to do from this point is how much correction we have to add to the initial start value. How much correction we have to make for the initial start value in order to get the functional value equals to capital F. Okay, to calculate it, I am going to expand f of x naught plus delta x. F of x naught plus delta x we are going to expand by using Taylor's series. Okay, yeah. So let's write here by Taylor's series. F of x naught plus delta x I am going to expand. Yeah, just go through it. Is equals to f of x naught plus dou f by dou x value at x naught into delta x by 1 factorial plus dou square f by dou x square at x naught into delta x whole square by 2 factorial plus and so on, like this way. F of x naught is dou f by dou x at x naught plus dou square f by dou x square x naught delta x whole square by 2 factorial plus and so on. Okay, listen here. In this again, we are going to neglect the higher order terms. Means this delta x square, delta x cube, delta x power 4. These higher order terms we are going to neglect. These are higher order terms which are neglected. Okay, next, listen please, listen kindly. See, from this, you can say this f of x naught plus delta x value, how much? F of x naught plus delta x value is equal to capital F number, whatever they have given in the data. This is nothing but f of x naught plus delta x is nothing but capital F value, whatever they have given in the data. Yes or no? What is f of x naught value? This is the number we calculated. f of x naught is a number what we calculate. Okay, so the first number what we have, f of x naught plus delta x value, I will say f specified in the data. F value specified in the data. So I will say the change in all places here. F of x equals to capital F specified value. X naught we have assumed. F of x naught is equals to capital F specified. Then x naught is a solution. F of x naught is not equals to capital F specified. Then we should add correction delta x to this in order to get the capital F specified. Okay. So in the next slide, I will say it is a capital F specified value. And f of x naught, what we have here is a capital F calculated value. Capital F calculated value. Now we can say from this equation, delta x, so-called correction, delta x, that is a correction, which is equals to specified value of the function minus calculated value of the function by what you can say dou f by dou x at x naught. Dou f by dou x at x naught, this one. So this is a correction to be made in the state. Correction to be made in the state. Okay, listen to me again. This procedure, you might have studied this procedure maybe in numerical methods also, right? Very simple. First, we'll take some initial start. With that initial start, we go for calculated value of the function. Calculated value of the function. Similarly, differential value of the function at that state. Following, then we calculate the correction. After getting correction, we add this correction to x naught value, we get the updated state. New state we get. New state value we get. With that new state value, calculate again function value, capital F calculated, calculate the differential value, and then calculate the correction again. With that correction, add that correction to the previous state, we get the updated state again. With that updated state, again you go for function calculated value, differential value, again delta x. Like that we have to repeat. How far we have to repeat this one? How far we have to repeat this one? Anybody tell me please? Up to the point, the same values got repeated. Up to the point, the same values are getting repeated. Up to that point, you have to repeat this calculation, so-called the iterations. Right? Means up to the point wherever you are going to get this delta x value coming close to 0. Delta x value coming close to 0. Up to that point, we have to repeat these iterations. And at that point, we say we are meeting the convergence. Yes. All of you getting this method? Simple one. Simple. Now, with the same basic what we have studied now, I will be extending this for 2 states. Means I can say the next heading as NR method with 2 state variables. NR method with the 2 state variables. NR method with 2 state variables. Two state variables. I can call these 2 states variables as x1, x2 for time being. 2 state variables I am calling as x1 and x2. X1, x2. Okay. Now what I can say is, let we have 2 nonlinear algebraic functions. Let we have 2 nonlinear algebraic equations. Nonlinear algebraic equations. So the 2 nonlinear algebraic equations are f1 of x1 comma x2 is equal to capital F1. Second one, f2 of x1 comma x2 is equal to capital F2. That capital F1, capital F2 are specified values. Capital F1, capital F2 are specified values. Given in the data. F1 of x1 comma x2, capital F1 specified. F2 of x1 comma x2 is capital F2 specified. Similar procedure what we have taken earlier. Let us take initial start for the x1 and x2. Let initial state values or initial guess also you can write for states initial guess for the states are x10 comma x20. Initial guess for the states are x10 comma x20. After taking this initial guess, substitute these initial guess values in the functions. So let's calculate. Let us calculate. Next step I am writing. Calculate f1 of x10 comma x20 and f2 of x10 comma x20. You calculate these two values. After calculating these two, what you should say? Check whether these values are equals to the specified values given in the data or not. Okay, fine. So I'll show in the next slide. Yes, it is there for GATE exam. So if function value f1 of x10 comma x20 is equals to capital F1 specified number and f2 of x10 comma x20 is equal to capital F2 specified number, then solution for states will be x10 comma x20. Solution for the states will be x10 comma x20. Okay. Next thing. But most of the times it won't happen, as I said you earlier. So I can say if f1 of x10 comma x20, it is not equals to f1 specified. If it's not equals to f1 specified, or f2 of x10 comma x20 not equals to f2 specified. If any one among these two is not satisfied, then add corrections. Delta x1 comma delta x2. Add corrections delta x1 comma delta x2 to x10 comma x20. The values of x10 comma x20 such that what you should say, f1 of x10 plus delta x1 comma x20 plus delta x2 will be equals to the value of f1 specified, f2 of x10 plus delta x1 comma x20 plus delta x2 is equal to f2 specified, right? f1 of x10 plus delta x1 comma x20 plus delta x2. Similarly, f2 of x10 plus delta x1 comma x20 plus delta x2 is equal to f2 specified. Now we have to expand these two functions. By using Taylor series. And after expanding them, we try to get the values of delta x1 and delta x2. That's it. That's a simple procedure what we are following. Yeah, you please complete it. I will move to next slide. And I will say by Taylor series expansion. Okay, so I'll say by Taylor series expansion. So f1 of x10 plus delta x1 comma x20 plus delta x2. f1 of x10 plus delta x1 comma x20 plus delta x2. This we are going to write as f1 of x10 comma x20. f1 of x10 comma x20 plus series function dou f1 by dou x1 at x10 x20 into delta x1 by 1 factorial plus dou f1 by dou x2 at x10 x20 into delta x2 by 1 factorial plus and so on. This one. Next function I am saying F2 of x10 plus delta x1, comma x20 plus delta x2 is equal to F2 of x10 comma x20 plus dou F2 by dou x1, x10 x20 into delta x1 by 1 factorial plus dou F2 by dou x2. This is at x10 x20 into delta x2 by 1 factorial plus and so on and so on. All of you getting this? Whatever the higher order terms you are getting now, so called second differential, third differential, whatever you get now, those higher order terms we are going to neglect. Whatever the higher order terms we are getting now, those higher order terms we are going to neglect. Let me write in a simple way. Second order and third order, whatever the terms you get now, these are higher order terms which are neglected. Higher order terms which are neglected. Okay, next. Listen, please. Listen. Simple thing. It's an extension to the previous one, as I said. What is this F1 of x10 plus delta x1, x20 plus delta x2? It is the value capital F1 specified. That's the value capital F1 specified. And this F1 of x10, x20 is a capital F1 calculated value. Calculated value of the function. And this is capital F2 specified. And this is capital F2 calculated. Capital F2 calculated value. Okay. These are calculated values of the function. These are specified values of the function. Now the first equation you can rewrite. First equation you can rewrite. F1 specified minus F1 calculated. Dou F1 by dou x1 into delta x1 plus dou F1 by dou x2 into delta x2. Second one. F2 specified minus F2 calculated. You will get that function. Let me move. F1 specified minus F1 calculated is equal to dou F1 by dou x1 into delta x1 plus dou F1 by dou x2 into delta x2. Of course, these differential values are at the initial states. Differential values are at the initial states only. I have not written it, but still you have to remember. Next one. F2 specified minus F2 calculated. You take up this function, you will get like dou F2 by dou x1 delta x1 plus dou F2 by dou x2 delta x2. Dou F2 by dou x2 delta x2. And you see, F1 specified minus F1 calculated, this is the value delta F1. F2 specified minus F2 calculated, this is a value delta F2. F1 specified minus F1 calculated delta F1. F2 specified minus F2 calculated is delta F2. Now, I will try to rewrite this into a matrix form. I'll try to rewrite this into a matrix form. Delta F1, delta F2 here. Delta F1, delta F2 is equal to, So this matrix you will get like dou F1 by dou x1, dou F1 by dou x2, dou F2 by dou x1, dou F2 by dou x2. This multiplied with correction delta x1, delta x2. Delta x1, delta x2. Like this, we are going to get the matrix. Okay. So please write it. I will come back within 1 minute. So look here, look here. Say whatever the delta F1, delta F2 matrix we have here, delta F1, delta F2, that we are going to call as mismatch vector, right? Or we can say sometimes as error vector also. Let me copy this one to the next slide. So that here. So this delta F1, delta F2 matrix, what we have here, it is going to be called as mismatch or error vector. Mismatch, or you can call it as error vector, or you can say matrix. Okay, see this delta x1, delta x2, delta x1, delta x2 column vector, what we have, this is going to be called as correction vector. Okay, state correction vector. Delta x1, delta x2 is going to be called as correction vector. See, listen. Whatever the relationship we have between these two, this matrix, what this matrix is consisting here? Slopes. This matrix is consisting slopes, and this can be called as gradient matrix. Gradient matrix or gradient vector, or you can call this as sensitivity matrix, particularly first order sensitivity matrix. First order sensitivity matrix. Sensitivity matrix. Like this you can call. Else you can say sometimes this as Jacobian matrix or Jacobian vector. Jacobian matrix, or you can say Jacobian vector. We'll call this as J. We'll call that with a letter J. Okay. And this delta F, what we have now? Delta F vector, I am calling simply like this, delta F. Okay. And this correction vector, we are going to call it as delta X. Correction vector, we are calling as delta X. From this one, you can write mismatch vector is equals to Jacobian multiplied with delta X. Mismatch vector delta F is equal to Jacobian matrix multiplied with correction vector delta X. See, from this, listen please, listen all of you. From this, I know the mismatch vector already because I know F specified value as well as F calculated values. F specified value they will give in the data. F calculated value we can calculate it. So this matrix I know, delta F matrix I know. Jacobian matrix also I know, because simple. I know functions. I will differentiate the functions. I will substitute the states. Whatever the known values here, that I will substitute. So that I know this, what we call Jacobian matrix also. Only the vector what you have to calculate is correction. Okay. So what you get the correction vector from this now? Delta X correction vector is nothing but Jacobian inverse into delta F. Jacobian inverse into delta F. Okay, let us see the sizes of these matrices quickly. Sizes of these matrices. What is the delta F size you have? What's the size of delta F? 2 by 1. 2 by 1. And what is the Jacobian size? 2 by 2. Delta X, 2 by 1. Let me write. It's of 2 by 1 size. It's of 2 by 2. It's of 2 by 1. What is that number 2? What is that number 2 here? Number 2 is a number of equations to be solved or number of states to be calculated. Number 2, what we have here is number of equations to be solved as well as number of states to be calculated. Okay, for example, if you want to calculate n states, n unknown states, you write n unknown states. At that time, you have to solve n equations. Okay, let me write that. To find out n unknown states, n equations has to be solved. N equations has to be solved. Okay, so in this case, NR method formulation will be NR method formulation will be, yeah, check this one. Same equations I will repeat. delta F is equal to Jacobian matrix into delta X. Same equation I have repeated. Delta F equals to Jacobian matrix into delta X. Can you tell me what is the delta F size here? What is the size of delta F? N, so it will be N by 1 size. What is the delta X size? Also N by 1. And Jacobian size will be obviously N by N. Jacobian size will be N by N. From this, the correction vector delta X is equals to Jacobian matrix inverse into delta F. Jacobian matrix inverse into delta F. Okay, you please go through this one. The same thing what we are discussing now, I'm going to extend to the load flow. So called the power flow analysis. Okay. See, the same thing what we are discussing now, I'm going to extend for the load flow. Yeah. So I'm sorry. Listen here. See, the power equations what we are going to solve in case of Newton-Raphson method. In case of Newton-Raphson method, that I'm going to write here. Just listen. Power equations to be solved in NR method. Power equations to be solved in NR method. NR method. See, at the beginning, we have discussed about basic power flow equations, right? We have discussed about basic power flow equations, so-called PI. Ith bus real power injection equals to sigma K equals to 1 to N VI VK YIK VI VK YIK cos of theta IK plus delta K minus delta I. Theta IK plus delta K minus delta I. Okay, and QI will come to be minus sigma K equals to 1 to N VI VK YIK sin of theta IK plus delta K minus delta I. Theta IK plus delta K minus delta I. So these are the equations what we are interested to solve actually. These are the equations what we are going to solve actually. This is a last topic. This is a last topic. NR method we'll discuss briefly. We will be concentrating on the Jacobian signs. Okay. After that, this method I will extend to decoupled load flow and fast decoupled load flow. That's it. At the end, we'll discuss about the differences between the methods. Okay. Yeah. Listen to me. Already I said you this statement. This real power is a function of mod V and delta. Today will be the last class. Maybe within 2 hours we will finish the syllabus. Q is again a function of mod V comma delta. Okay, first function 1, function 2 I am treating. Okay, next thing. Let us take some numerical example in order to catch up this Jacobian size and all first. I'll take a 3-bus system as an example. I'll show in the next slide. 3-bus system I am taking as an example. Example number 1 you take. Okay, 3-bus system. 3-bus system. So in that, bus number 1 is a slack. Bus number 1 slack. Bus number 2 is a PQ. Bus number 3 is a PQ. Like this way. Bus 1 slack bus, bus 2 PQ, bus 3 also PQ. Okay, done. Tell me now. Listen. Be cool. Just listen whatever I am saying. Okay. How many states we have total? Means bus 1 delta 1 mod V1. Bus 2 delta 2 mod V2. Bus 3 delta 3 mod V3. These are the total number of states available. Total 6. 6 states are available. Okay. Yeah. Look here. States of the system. States of the system. Delta 1, delta 2, delta 3, mod V1, mod V2, mod V3. These are the states of the system. Next thing. In these 6 numbers, which are the known and which are the unknown? Which are the known states and which are the unknown states? Could you please tell me which are the known states here? Tell me please. Which are the known states in these 6 known states? Nobody is answering. Tell me please. Which states you know? Only delta 1 and V1 are known. Delta 1, V1 are known because bus 1 is a PV bus, sorry, slack bus. Bus 1 is a slack bus. Delta 1, V1 will be known for us. Okay, delta 1, V1 will be known. Bus 2, PQ, I don't know angle and voltage magnitude. Bus 3, again PQ, I don't know voltage magnitude. So, what are the unknown states now? What are the unknown states here? Unknown states will be bus 2 voltage angle, bus 3 voltage angle. Bus 2 voltage magnitude, bus 3 voltage magnitude. Delta 2, delta 3, mod V2, mod V2. Mod V2, mod V3. These are the unknown states. Okay, done. Next, listen. What are the equations we are capable to use? What are the equations available? That I will tell. Okay, just don't think about the procedure and all. Just listen to the words, whatever I am saying you will get some clarity. Tell me, bus 1, P1, Q1. Bus 2, P2, Q2. Bus 3, P3, Q3. Total, how many equations we have? 6 equations we have. Okay, done. Let me write. Equations. Equations will be real power at bus 1, reactive power at bus 1. Real power bus 2, reactive power bus 2. Real power bus 3, reactive power bus 3. Like this, we'll have total 6 equations. P1, Q1, P2, Q2, P3, Q3. Yeah, listen. For example, if you want to take up the NR method formulation, you know this vector delta F equals to Jacobian matrix into delta X. Delta F equals to Jacobian matrix into delta X. I am asking one very simple question to you. What this delta X will be consisting generally? I need your response now. What the delta X will be consisting? Corrections in the states. Corrections in the states. Corrections in the states means what? That will be consisting delta values, delta mod V values. Delta X will be consisting delta values and delta mod V values. And what this delta F will be consisting? Mismatch vector, or you can say error vector. What that error vector will be? Error in the real power, error in the reactive power. Error in the real power, error in the reactive power. Yeah, very simple thing. Earlier, we have functions like F1, F2, F3 and so on up to Fn. But now, we have functions like P1 function, P2 function, P3 function, Q1, Q2, Q3. That's it. So, how many mismatches you can expect now? Delta P1, delta P2, delta P3, delta Q1, delta Q2, delta Q3. All of you getting this or not? Tell me, all of you. Please tell me. Delta P1, delta P2, delta P3, delta Q1, delta Q2, delta Q3. These are the mismatches. What do you mean by delta P generally? It is simply specified value of the real power minus calculated value of the real power. Delta Q is what? Specified value of reactive power minus calculated value of the reactive power. Delta P equals to specified value minus calculated value. Delta Q also specified value minus calculated value. Very simple question. To have a possibility of delta P1 calculation, we should write P1 specified minus P1 calculated. Delta P1 equals to P1 specified minus P1 calculated. Do you know the P1 value specified? Do you know the P1 specified value? Yes or no? That they have to give in the data, right? Specified value means they have to give in the data. At the bus 1, do you know the real power? Yes or no? No, we don't know the P1 specified value. If that is the case, listen all of you. If that is the case, I can't use a P1 equation. The reason is I can't find out the delta P1. Real power mismatch at bus 1, I can't calculate. I don't know whether you have understood this logic or not. Are you clear? Okay. Can I use P2 equation now? Can I use P2 equation? What is P2 equation? P2 specified minus P2 calculated. P2 specified minus P2 calculated. Can I use it? Yes. Bus 2 is a PQ bus, right? Bus 2 is a PQ bus means definitely they will give the value of real power in the data. So calculated value, I can do it. Calculated value, I can do it. There is no issue with that. So delta P2 we are capable to know. So I can use a P2 equation safely. P3 equation, yes. Why it is so means P3 value they have given in the data. Okay. Q1, can I use Q1 equation? Yes or no? Can I use Q1 equation or not? Yes or no? No. What's the reason? Because I don't know the value of Q1, I can't find out the value of delta Q1 here. So I can't use a Q1 equation. Can I use Q2? Yes. Can I use Q3? Yes. Because bus 1, bus 3 both are PQ buses. So obviously I know the values of Q2 and Q3. So total, how many equations are possible to solve? How many equations are possible to solve? Anybody? How many equations we are capable to solve here? 4. 4. Okay. How many states you have to calculate? How many states you have to calculate? Unknown states. Again 4. So 4 equations, 4 unknown states. 4 equations, 4 unknown states. By solving it, we have to get those 4 unknown state values. Following all of you? So now let us write the NR method formulation for this problem. NR method formulation I am going to write. NR method formulation. Yeah, look here. We have to write mismatches in the real power, delta P2, delta P3. Mismatches in the reactive power, delta Q2, delta Q3. That's a delta F vector. That's a delta F vector. So I can say NR method formulation. Here I will say delta P2, delta P3, and then delta Q2, delta Q3. These are power mismatches, real and reactive power mismatches equal to. So you no need to bother about the Jacobian matrix. We will fill that matrix. It's very easy to fill this matrix. And what about the correction vector? What about the correction vector here? That will be delta delta values, delta delta 2, delta delta 3 correction, delta mod V2, delta mod V3 correction, delta delta 2, delta delta 3 correction, delta mod V2, delta mod V3 correction. Like this will be it. Okay, next. So this was a Jacobian matrix. It was a Jacobian matrix. First element in the Jacobian. Very simple. Delta P2, delta delta 2. Delta P2, delta delta 2. Nothing but dou P2 by dou delta 2. So differentiation of P2 with respect to delta 2. Differentiation of P2 with respect to delta 2. Next element. Dou P2 by dou delta 3. Dou P2 by dou delta 3. Next element. Dou P2 by dou mod V2. Dou mod V2. Next one. Dou P2 by dou mod V3. Dou P2 by dou mod V3. Like this you will get. Next one. With respect to P3, if you see, with respect to P3. Dou P3 by dou delta 2. Dou P3 by dou delta 3. Dou P3 by dou mod V2. Dou P3 by dou mod V3. Clear? Differentiation of P3 with respect to delta 2, delta 3, V2, V3 is this row. Next one. With respect to Q2 is dou Q2 by dou delta 2. Dou Q2 by dou delta 3. Dou Q2 by dou mod V2. Dou Q2 by dou mod V3. Dou Q2 by dou mod V3. Okay, next thing. Q3. Dou Q3 by dou delta 2. Dou Q3 by dou delta 3. Dou Q3 by dou mod V2. Dou Q3 by dou mod V2. Like this, you will get the matrices. Clear? Elements. Simple. These are nothing but differential terms. Differential terms. And what is the size of Jacobian matrix now? What is size of Jacobian matrix? 4 by 4 matrix. Jacobian matrix will be 4 by 4 size. Okay. What is the number 4 here? What is the number 4? Number of unknown states or number of equations to be solved. Both are equal to 4. Number of unknown states equal to number of equations to be solved. Number of equations to be solved. And that number right now it is 4. So the Jacobian size will be 4 by 4. Jacobian size will be 4 by 4. 4 by 4. Okay, done. Next thing. Let's take one more example. So that is the example number 2 I will take. Second example I am taking up for our clarity. Taking one more example. Example 2. Let's say 5 bus system here. 5 bus system. So in this 5 bus system, bus number 1, it's a slack bus. Not slack. I will give some other name. PQ bus you take. Bus number 1 is a PQ bus. Bus 2, I am saying it is a PV bus. PV bus. And bus number 3, it's a slack bus. Bus number 3 is a slack bus. Bus number 4, it's a PQ bus. Bus number 5, it's a PV bus. Like this we can say. Simple. Bus 1 PQ, bus 2 PV, bus 3 slack, bus 4 is PQ, Bus 5, we have a PV bus. Okay. Total number of states will be 10. 10 states. Delta 1 V1, Delta 2 V2, Delta 3 V3, Delta 4 V4, Delta 5 V5. Okay, 10. You don't need to write them. Directly, you try to identify which are the unknown states. Directly, you try to identify which are the unknown states. Unknown states. Unknown states. Simple. Just look here. Unknown states. Bus 1. Bus 1. I don't know angle as well as voltage. I don't know angle value as well as the voltage magnitude value. Delta 1 V1 will be unknown at the bus. Bus 2. Bus 2 is a PV bus now. PV bus means voltage magnitude already you know and you don't know the angle. That's it. Only delta 2 is unknown. Mod V2 is known value. Bus 3, slack. I know both delta 3, V3. Delta 3, mod V3, both values I know at the bus 3. Bus 4, PQ. PQ means again, I don't know angle as well as the voltage. Delta 4, V4. I don't know these two values. Delta 4 I don't know. Mod V4 also I don't know. Bus 5, PV bus. PV bus in the sense, delta 5 is unknown. Mod V5, known value. All of you getting this one? Tell me please, all of you getting how to write the unknown states? I need your response. Very simple, very simple. Except the slack bus, at all other remaining buses, you should find out the angle. Except the slack bus, at all other remaining buses, you have to find out the angle. Right? At PQ buses, you should find out the voltage magnitude. PQ buses means 1 and 4, mod V1, mod V4. That's it. Okay. Now you have to pick up the equations in a proper way. Equations. Total, how many equations we have? 10. Let me write. P1, P2, P3, P4, P5, P4, P5. And similarly, reactive for equations 1, 2, 3. 1, 2, 3, 4, 5. Okay, these are 10 equations available. 10 equations. In these 10 equations, which equations we have to pick up? In these 10 equations, which equations we have to pick up means whichever the real and reactive powers we know, those equations we have to pick up. Bus 1, I know both real and reactive powers because it is a PQ bus. So I can use both P1, Q1. Bus 2, PV bus. So I can use only P2, I can't use Q2 equation. Bus 3, slack. I don't know both real and reactive powers, so I can't use P3 and Q3. Bus 4, PQ. I know both P and Q. P4, Q4 I can use. Bus 5, I can use P5, but I can't use Q5. How many equations we are capable to solve now? 1, 2, 3, 4, 5, 6 equations. 6 unknown states. What's the size of Jacobian? 6 by 6. Jacobian size will be 6 by 6 matrix. Okay, let's write. Let's write that NR method formulation. Let's write the NR method formulation. So I'll say here NR method formulation. NR method formulation. First, I have to take the mismatches. Mismatches in the powers. Delta P1, delta P2, delta P4, delta P5, delta Q1, delta Q4. Right. Delta P1, delta P2, delta P4, delta P5, delta Q1, delta Q4. So these are the real and reactive power mismatches. Real and reactive power mismatches, and this is a Jacobian matrix. So I have to show Jacobian matrix here. Okay, and here I will be showing the corrections. I will be showing the corrections here. Just check this one. Check these corrections. What I have to write? Delta delta 1, delta delta 2, delta delta 4, delta delta 5. Corrections in the angles. Corrections in the angles. Okay, next. Corrections in the magnitudes of voltages. Corrections in the magnitudes of voltages. Like this. Now, elements in this Jacobian I have. Elements in this Jacobian. First element you observe. Dou P1 by dou delta 1. First element is dou P1 by dou delta 1. Next element, dou P1 by dou delta 2. Next, dou P1 by dou delta 4. Next, dou P1 by dou delta 5. Dou P1 by dou mod V1. Dou P1 by dou mod V5. Sorry, V4. All of you understood this row? First row, simple differentiation of real power P1 with respect to the states, unknown states, unknown states. Okay, here you get dou P2 by dou delta 1, dou P2 by dou delta 2, dou P2 by dou delta 4, dou P2 by dou delta 5, dou P2 by dou V1, dou P2 by dou V4. Like that you get with respect to P4 also in this way and P5 also in this way. I'm not writing them. I'm not writing. It's very easy to write now. With respect to Q1, I will write dou Q1 by dou delta 1. Dou Q1 by dou delta 2. Dou Q1 by dou delta 4. Dou Q1 by dou delta 5. Dou Q1 by dou mod V1. Dou Q1 by dou mod V4. Similarly, with respect to Q4 also, with respect to delta 1, delta 2, delta 4, delta 5, V1, V4. Like this we can say. Right? So I think all of you getting how to write this Jacobian matrix now? All of you getting how to write this Jacobian matrix? Yes. Now, so as a conclusion from this point, as a conclusion or an extension from this point, just listen. I'm dividing this power mismatch vector into two parts. First part is delta P, real power mismatches. Second part is a delta Q, reactive power mismatch. Yeah. So it's a delta P vector and it's a delta Q vector. And you see this side, it's a delta delta correction vector and it's a delta mod V correction vector. Delta delta correction vector, delta mod V correction vector. Yeah. I said already anonymous attendee. How many topics left, sir? Please say. I said this is the last topic in the power system analysis. Yeah. Next thing. I will divide this whole matrix into number of parts here. Like this, I am dividing, not arbitrarily, but in a proper way. First matrix, what I have shown here, it's a differentiation of real power with respect to delta. And this matrix is differentiation of real power with respect to voltage magnitude. Differentiation of reactive power with respect to delta. Differentiation of reactive power with respect to voltage magnitude. Differentiation of reactive power with respect to angle, voltage magnitude. Similarly, real power with differentiation with respect to delta as well as voltage magnitude. Let me rewrite this whole matrix. So I'm moving into the next slide. Something like this. So delta P, delta Q vector. Other side you get dou P by dou delta, dou P by dou mod V, dou P by dou delta, dou P by dou mod V. And here you get dou Q by dou delta. And it is dou Q by dou mod V. And this multiplied with what you can have delta 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 mod V. Delta 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 mod V. Like this you can say. Delta P delta Q. And then here dou P by dou delta, dou P by dou mod V, dou Q by dou delta, dou Q by dou mod V. Dou mod V. Just I will give some names for these matrices, submatrices of Jacobian. Right? This matrix I will name it as J1 matrix. This I will call J2 matrix. This is J3 and this is J4. As a whole, this J1, J2, J3, J4 is going to be called as Jacobian matrix. As a whole, we will call this as Jacobian matrix. Okay. Now, calculating the size of this Jacobian is very important with respect to examination. Not only with respect to GATE and the ESC, with respect to any examination, calculating the size of Jacobian is more important. One more thing, whatever the method we are discussing here, let me write at the beginning itself. Okay, this one. So the method what we are doing here is method in polar coordinates. NR method in polar coordinates. Completely. Till now, whatever the discussion we have done in the NR method for load flow analysis is a NR method in polar coordinates. Okay, I want to find the Jacobian size in a generalized way. In a generalized way. Just observe now. Observe. Generalization. You write simply. Generalization. Let us say we have n number of buses in the system. Number of buses in the system are n, I will say. Number of buses equals to n. Next thing. Next thing. In that n buses, one bus will be slack, obviously. In those n buses, one bus will be slack bus. Number of PV buses, PV are generator buses, m. Number of PV buses are m. Remaining all will come in the category of load buses or PQ buses. So how many PQ buses you get now? It is n minus m minus 1. Na? Remaining buses will be n minus m minus 1. N minus m minus 1. These are the remaining buses, you can say, PQ buses. Okay, now, very simple question to you. Method one in the Jacobian calculation I am writing. Method 1. Method number 1. Okay, tell me please. How many angles we have to calculate here? How many angles we have to calculate? Number of deltas to be calculated are unknown. Number of deltas unknown. Anybody tell me please? In this generalization, Ankur, I am asking you in this generalization, how many angles we have to calculate? Except at the slack bus, at all other remaining buses, we have to calculate the angle. N minus 1. Anil, listen. Except at the slack bus, at all other remaining buses, we have to calculate the angle. So how many deltas unknown here? N minus 1 deltas will be unknown. How many voltage magnitudes unknown? How many voltage magnitudes unknown now? Tell me please. At how many buses we have to calculate the voltage magnitudes? At only PQ buses, right? At only PQ buses, we have to calculate the voltage magnitude. That will be n minus m minus 1 voltage magnitudes we have to calculate. Okay, now tell me, what is the total number of unknown states? Number of unknown states. Unknown states. That will be number of deltas n minus 1 to be calculated plus number of voltage magnitudes n minus m minus 1 to be calculated. It will come to be 2n minus m minus 2. 2n minus m minus 2. And what is the Jacobian size you can guess from this point? What is the Jacobian size you can expect here? 2n minus m minus 2 by 2n minus m minus 2. That will be the size of the Jacobian matrix. 2n minus m minus 2 by 2n minus m minus 2. That is the Jacobian size. This is one way. This is one way. I'll say method 2. Method 2. Just listen. Equations. In the way of equations, I will discuss in method 2. Moving to next slide. Method number 2. Method number 2. Yeah. What are the real power equations we are capable to solve? Real power equations capable to solve. Real power equations to be solved. Can be solved. How many? At how many buses you know real power? At how many buses you know real power? Except the slack. Except the slack. At all other remaining buses you know real power? Except the slack, at all other buses, we know the real power value. At m buses, you know real power. At n minus m minus 1 also, you know the real power. Total, how many real powers you know? N minus 1. So, n minus 1 real power equations we can solve. How many reactive power equations to be solved? How many reactive power equations we can solve? Tell me, please. That will be only PQ buses. That will be only PQ buses. How many we have? N minus m minus 1 reactive power equations we can solve. N minus m minus 1 reactive power equations we can solve. And what are the total number of equations to be solved here? Total number of equations that can be solved. Can be solved equal to n minus 1 plus n minus m minus 1. So it will come to be 2n minus m minus 2n minus m minus 2. And by this, again, you can say the Jacobian size will be 2n minus m minus 2 by 2n minus m minus 2. These are two methods, two techniques of calculating the Jacobian size. Whichever the way you are comfortable, you can go with that. Whichever the way you are comfortable, you can go with that. But in some cases in the exam, they used to ask the submatrices sizes also. What is size of J1 matrix? What is size of J2? What is size of J3? Like that they will ask. Okay? Yeah, I will be showing you. I will be showing you about that J1, J2, J3, J4 submatrices sizes now. Very simple to write. I'll show in the next slide. We know already formulation. Delta P, delta Q is equal to submatrices of Jacobian. J1, J2, J3, J4 submatrices. And here you have corrections in the angles, corrections in the voltage magnitude. Corrections in the angles and corrections in the voltage magnitudes, you can say. Okay, simple. Just answer to the thing. Answer this one. How many delta P's you have? How many real power mismatches you have? Anybody? How many real power mismatches you have? N minus 1. How many real power mismatches you have? That will be n minus 1. You are saying, Sivanath. What happened, Sivanath? How many real power mismatches we have? N minus 1. That is nothing but number of real powers known, right? How many number of real powers you know? N minus 1. So obviously mismatches will be n minus 1. How many delta Qs you have? How many delta Qs? Tell me please. How many delta Qs? N minus m minus 1. Delta Q values will be n minus m minus 1. Rather than that, I will write this is number of PQ buses. Because at how many buses you know reactive power? PQ bus only, na? PQ bus only, right? So I will write simply NPQ, number of PQ buses. That's a better word, even to say n minus m minus 1. Okay, now tell me please. How many deltas you have to calculate? How many angles you have to correct? How many angles you have to correct? N minus 1. How many voltages you have to correct? How many voltages do you have to correct? N minus m minus 1. Else you write NPQ. Number of PQ buses you can write in a simple way. Number of PQ buses. Okay, now listen here, listen. This J1 vector size is what? What is the size of the J1 matrix? J1 matrix. That is nothing but relation between delta P, delta, delta. Relation between delta P and delta, delta. What is its size now? N minus 1 by N minus 1. This vector size will be N minus 1 by N minus 1. All of you getting it? Tell me please. What is size of J2 matrix now? What is size of J2? Relationship between what? Delta P and delta B. Delta P and delta B. And what is size now? N minus 1 by NPQ. Is this side N minus 1, this side NPQ. So it will come N minus 1 by NPQ size. N minus 1 by NPQ size. What is J3 size? J3 giving relation between delta Q, delta, delta. Delta Q, delta, delta. What is that size now? NPQ by N minus 1. NPQ by N minus 1. J4. What is the J4 size? Delta Q, delta mod B. So it will come NPQ by NPQ. NPQ by NPQ. Like that, you are capable to calculate the sizes of remaining matrices available. J1, J2, J3, J4 submatrices. Yeah, next. So one simple observation from this point is J1, J4. These two will be square matrices. N minus 1 by N minus 1, NPQ by NPQ. What about J2, J3? May or may not be square. Because that depends upon NPQ values, strictly speaking. N minus 1 anyhow constant. NPQ, that depends. How many PV buses you have, that will decide. Okay. So in that perspective, some conclusions I am taking up here. Some conclusions. Simple. J1 and J4. These two are always square matrices. Always square matrices. But you see J2 and J3, these two may or may not be square. May or may not be square. Or you can say these matrices are sometimes rectangular matrices. These matrices are sometimes rectangular matrices. J2, J3 will be rectangular matrices. Yeah. Okay. Next thing. So let's take some small problems on this Jacobian size and all. Okay. So I'll say in the next slide. So let's see some questions. It's a previous GATE examination question. Look this one. Previous GATE exam question. Go through it. Okay. A power system consists of 300 buses, out of which 20 buses are generator buses. 25 buses are ones with the reactive power support. 20 buses are ones with the reactive power support. And 15 buses are the ones with fixed shunt capacitors. Fixed shunt capacitors. All other buses are load buses. Okay. It is proposed to perform the load flow analysis in the system by using Newton-Raphson method. The size of Newton-Raphson Jacobian matrix is in bracket polar coordinates. We are discussing polar coordinates only. So the same procedure what we are discussing, that we can move ahead. Rectangular I will discuss little. Rectangular coordinates also I will discuss little. Okay, just go through it first from the data what they have given. Power system consisting how many buses total? 300. N equals to 300. See in that 20 buses having generators. Anything mentioned regarding slack in the problem? In the problem, anything mentioned regarding slack? No, it didn't mention anything about slack. So in that 20, one bus you should take as slack. Remaining 19 will be generator buses. So one bus you should take as slack, and in the remaining what that 20 we should take 19 as a PV. 19 as PV buses. Next thing. 25 buses are with reactive or support. Means which bus is that? Reactive or support in the sense which bus? I need your response, please. Reactive or support means which bus? That will be obviously PV bus. That will be obviously PV bus. So I can say 25 buses will come in the category of PV. You write here it is Q support. Q support. Next thing. 15 buses are the ones with fixed shunt capacitors. 15 buses are the ones with fixed shunt capacitors. So that will come in the category of PQ. 15 fixed shunt capacitors. Fixed shunt capacitors. Remaining all buses are load buses. Remaining all buses are load buses. Tell me now, how many buses still left here? 25 plus 15, that will be 40 plus 20. 40 plus 20, 60. Means remaining 240 will come in the category of PQ. Remaining 240 will come in the category of PQ. So what's the number of buses here? PV, how many you have? 44, I think. Okay. And this will be 255. 255. Tell me now, it's a very simple thing. Q support means it's a Q control bus, right? Voltage control bus. Q support in the sense it's a voltage control bus. Voltage control bus will come in the category of P. Tell me now, how many deltas you have to calculate? Deltas unknown. How many? How many deltas? 299 deltas you have to calculate. How many voltages you have to calculate? Mod V is unknown. Tell me please, I need your answer. How many voltages unknown? That will be PQ buses. 255. 255. What is summation of these two? So-called total number of unknowns. It will be 554, I think. 554 voltages unknowns. So total number of unknowns. Total number of unknowns will be 554. What's the size of Jacobian now? 554 by 554. 554 by 554 is the size of Jacobian. All of you getting this? All of you getting this one? Jacobian size will be 554 by 554. Yeah. So what's your answer now? That is option D is a correct one to be selected. Option D is a correct one to be selected. Simple question. Next. One more question I am going to take up in the next slide. So it's also a previous GATE examination question only. It's also previous GATE exam question. Just go through it once. Yeah, see that? See this question? A 10 bus power system consists of 4 generator buses indexed as G1, G2, G3, G4 and 6 load buses indexed as L1, L2, L3, L4, L5, L6. The generator bus G1 considered as slack. Generator bus G1 is considered as slack. And load buses L3, L4 are voltage controlled buses. The generator at bus G2 cannot supply the required reactive power demand. G2 generator can't supply the required reactive power demand. And hence, it is operating at its maximum reactive power limit. Operating at its maximum reactive power limit. The number of nonlinear equations required to be solved in the load flow problem using Newton-Raphson method in polar form is Newton-Raphson method, polar form how many number of equations we have to solve? That's the question. Let's move. Let's move. We have a 10 bus system here. 1, 2, 3, 4 generators like this. Loads L1, L2, L3, L4, L5, L6. Okay, next. Look at the data. Generator bus G1 is slack. So this G1, it's a slack. Slack. Okay, next thing. Load bus is L3, L4 voltage control. L3 voltage control. L3, L4 voltage control. L3, L4 are voltage control. Okay, done. Next thing. Listen kindly. Listen kindly. See, generators, generator G2 can't supply required reactive power demand, and hence it is operating at its maximum reactive power limit. What's the meaning of that? G2 cannot supply the required reactive power demand, and we are setting that reactive power supplied by G2 equals to its maximum value. Means obviously that G2 generator, whatever you have there, that will be acting as a PQ bus. That G2 is going to act as a PQ bus, right? PV to PQ conversion was done. So this G2 will be PQ bus. G2 will be PQ bus. What about G3, G4? No information regarding G3, G4. These two we should consider as PV only. G3, G4 will stay at the PV category only. And what about L1? Load PQ. L2, load PQ. But you see L3, L4 voltage control buses. Voltage control buses means PV buses. Voltage control buses means these two will come in the category of PV. L5, PQ. L6 also PQ. Tell me now, what are the total number of PQ buses existing? What are the total number of PQ buses existing? Simple check. 1, 2, 3, 4, 5. 5 PQ buses we have in this. How many PV buses you have in the system? How many PV? 1, 2, 3, 4. 4 PV buses. How many slack we have? Only one. 1 slack, 4 PV, 5 PQ buses. 5 PQ buses. Okay. Now tell me, how many equations to be solved is the question. You write deltas unknown, how many? Deltas unknown. 9, 10 minus 1, 9. Magnitude of voltage unknown. Magnitude of voltage unknown. That will be PQ buses only 5. So 9 plus 5, 14. 14 unknowns means 14 will be the number of equations to be solved also. Number of equations to be solved. 14 will be number of equations to be solved. Yeah. So that's our answer. That is option A. Correct one is option A. Option A. Yeah. So let's take up one more problem. One more problem I'm going to take up. I'm showing you the next slide. Next question. This one. It's also previous gate examination question only. Option D. Yeah, go through it. Yeah, and in a 100 bus power system, there are 10 generators. In a 100 bus power system network, there are 10 generators. In a particular iteration of Newton-Raphson method of load flow technique, in polar coordinates, two of the PV buses are converted into PQ. Following all of you, two PV buses got converted into PQ. Then what will happen? See, if you read these four options, number of unknown voltage angles increase by 2, number of unknown voltage magnitudes increases by 2, like that you are getting. Means ultimately what you have to find is what will happen to number of unknown voltages and what will happen to number of unknown deltas. See, simple. If the PV buses are converting into PQ, listen to me please. PV buses got converted into PQ. Any change in the number of deltas? See, any bus is it a PV bus or PQ bus? You should calculate the angle. Number of deltas will be remain same. Unknown deltas will be remains same. So voltage angles will be remain same to be calculated. What about voltage magnitudes? Because of this conversion from PV to PQ, at PQ bus we don't know voltage magnitude, right? So voltage magnitude I have to calculate the PQ bus, means voltage magnitudes calculation should be increased by 2. Voltage magnitudes calculation should be increased by 2. Following all of you? So I'll write here the solution. If PV buses got converted into PQ buses, PV bus converted into PQ buses, then there is no change in the number of deltas unknown. There is no change in deltas unknown. Okay, but mod V is unknown, magnitude of voltage is unknown, will increase. Okay, magnitude of voltage is unknown, will increase. Tell me. So as two PV buses converted into PQ, two mod V's unknown will increase. But deltas will be remains same. So what is the correct option now? Remains unchanged. Option B is the correct one. The number of unknown voltage angles remains unchanged, but the number of unknown voltage magnitudes will be increased by 2. Correct answer from the options given will be B. Fine. I think it's easy. Yeah. Done. Next. What will happen to Jacobian size? Anybody please tell me? Because of this PV bus conversion to PQ. PV bus conversion into PQ, what will happen to Jacobian size? See, as you think about the total number of unknowns are increasing, right? If the total number of unknowns are increasing, definitely number of equations to be solved increases, Jacobian size also increases definitely. Following all of you. So I'll say that statement. Due to PV bus conversion into PQ, total number of unknowns increases. increases. So obviously you can say Jacobian size will increase. Number of equations to be solved also increases. Jacobian size also increases. Jacobian size also increases. Simple. Jacobian size also increases. This is one comment. Tell me now, what is the maximum size of Jacobian expected for a n-bus system? What is maximum size? Maximum size of Jacobian expected in n-bus system. N-bus system. Tell me please. Maximum size of Jacobian. See, actually, if you go with the Jacobian size formula. Go with the formula only. Jacobian size formula. You know, it is 2n minus m minus 2 by 2n minus m minus 2. It's the size of Jacobian. What that m you have denoted? M is nothing but number of PV buses, right? M is nothing but number of PV buses. For example, if that m equals to 0, m value is equal to 0, then what is this number? 2n minus 2. That's the highest value. That's the highest number of equations to be solved, obviously. For example, if we don't have any PV buses in the system, all the buses are PQ. One is slack. Except the slack, remaining all buses are PQ. So definitely at each and every bus, we have two unknowns to be calculated. Two unknowns to be calculated means the overall number of unknowns will become n minus 1 into 2. So it will be 2n minus 2. Following all of you. So the maximum size of Jacobian to be expected will be 2n minus 2 by 2n minus 2. 2n minus 2 by 2n minus 2. You write here. Maximum size for Jacobian occurs if m equals to 0. Okay, and it is 2n minus 2 by 2n minus 2. Maximum size of Jacobian expected will be 2n minus 2 by 2n minus 2. Okay, done. Next thing. So next, let's think about the NR method in rectangular coordinates quickly. The Jacobian size we are going to discuss. After that, we continue our extension with respect to polar coordinates. Yeah. So let's say in the next slide, NR method in rectangular coordinates. NR method. Rectangular coordinates. My aim is to calculate only Jacobian size in this one. My aim is to calculate only the size of Jacobian. That's it. Size of Jacobian. It's one of the very untapped area. We can expect question in this one in future, right? NR method in rectangular coordinates. Listen to me. Actually, voltage magnitude. Let's say mod VI. Sorry, VI. Voltage VI. We represented this voltage in case of polar coordinates like mod VI at an angle delta. Like this, we have represented voltage VI. We represent as magnitude mod VI and associated angle is delta in polar coordinates. Whereas in case of rectangular coordinates, this voltage VI, I am going to write it as AI plus JBI. Some real part and some imaginary part. Real part and imaginary part. Okay. Now, if you take a comparison between these two, you take up a comparison between our relationship between the polar and rectangular coordinates. First of all, magnitude of voltage mod VI is equals to square root of AI square plus BI square. Mod VI is equals to root of AI square plus BI square. Whereas the angle delta I, it will come to be tan inverse of imaginary part by real part. So AI by BI. Sorry, BI by AI. Like this you can say. Listen to my words. Mod Vi equals to root of Ai square plus Bi square. Delta I equals to tan inverse of Bi by Ai. I am asking you very simple question. Very simple question. Just answer. To calculate angle delta in the rectangular coordinates. In the rectangular coordinates here. To calculate angle delta, definitely we have to know real path as well as imaginary path. To calculate the angle, definitely we should know what is the real part and what is the imaginary part. Yes or no? Tell me please. Yes or no? Yeah. Next, again. To calculate the magnitude of the voltage. To calculate the magnitude of the voltage, definitely I should know what is the real part and imaginary part. To calculate magnitude of the voltage, definitely I should know what is the real part and the imaginary part. Means my intention is to tell you, to calculate angle, I should find out two quantities. I will have two unknowns. One is real part, next one is imaginary part. To calculate voltage magnitude also, I should calculate two numbers. One is real part of voltage, next one is a imaginary part of voltage. All of you getting this? I will write the statement. To find any value, either mod V or delta, the real and imaginary parts must be known. Real and imaginary parts must be known. Must be known. Real and imaginary parts must be known. Okay, done. Now let us consider an n-bus system. So taking up in the next slide. Taking up in the next slide. N-bus system I am taking. N-bus system. So in that one bus will be slack. One bus will be slack. Number of PV buses I will take M. Remaining will be number of PQ buses only, which is nothing but N minus M minus 1. Number of PQ buses will be N minus M minus 1. One slack bus, M PV buses, N minus M minus 1 are the PQ buses. Next, listen please. Listen please. See, one slack is okay. PV buses, M PV buses you have now. At a PV bus, how many unknowns you have? At a PV bus, how many unknowns you have? Tell me please. Voltage magnitude you know already. Delta value we have to calculate at the PV bus. Delta angle we have to calculate at the PV bus. Yes or no? To calculate the delta, we have to calculate the real part of voltage as well as imaginary part of the voltage. To calculate the angle delta, I should calculate the real part of voltage as well as the imaginary part of voltage. Tell me please, how many unknowns you have at the PV buses? How many unknowns we have at the PV buses? Anybody? Anybody? Yeah. To calculate M voltage angles, listen please, M voltage angles, definitely I should know M real parts, M imaginary parts. So obviously it will be 2M unknowns here. 2M unknowns. Tell me in the similar way, how many unknowns we have at the PQ bus? Say at the PQ bus, I have to calculate the voltage angle as well as the voltage magnitude. Voltage angle as well as the voltage magnitude. So if you calculate simply real and imaginary parts of voltage, and I was capable to find both numbers, right? Both numbers. Then how many unknowns you get at this bus? At this bus, the number of unknowns will be 2 into N minus M minus 1. So it is 2M minus 2M minus 2, like this. Now, could you please tell me, what are the total number of unknowns here? What are the total number of unknowns in the rectangular coordinates method? Total number of unknowns in the rectangular coordinates method. In the NR rectangular coordinates method. 2M plus 2N minus 2M minus 2. By doing cancellations, you get 2N minus 2. 2N minus 2. Okay, now what will be the size of Jacobian? 2n minus 2 by 2n minus 2. How many equations to be solved here? 2n minus 2. That's it. See, very simple thing in the rectangular coordinates. Very simple thing in the rectangular coordinates. Whether the bus is a PV bus or PQ bus, whatever it is, we have to find both real and imaginary parts of voltage. Whether the bus is a PV bus or PQ bus, doesn't matter. We have to find out both real and imaginary parts of the voltage. That's it. Okay, let's move. Let's move ahead. So I'll write here. So total number of unknowns we have written. So Jacobian size in the rectangular coordinates method will be 2n minus 2 by 2n minus 2 always. Tell me now whether the size of Jacobian depends upon the number of PV and PQ buses. Whether the size of this Jacobian is depending on the number of PV and PQ buses. No, whatever may be the number of PV and PQ, I should calculate 2n minus 2 numbers. So you write it is independent on NPV and NPQ. Number of equations to be solved. Number of equations to be solved. It will be 2n minus 2. Number of equations to be solved will be 2n minus 2. Yeah? Next thing. Next, I'll take one small problem on this rectangular coordinates quickly. Go through it. See this question once. A 183 bus power system has 150 PQ buses and 32 PV buses. 150 PQ, 32 PV. What is the total? 150 plus 132, it is 182. One bus he left. One bus he left away, that's a slack. Whatever the bus he left from this classification, that will be slack. Okay, next. In the general case, to obtain the load flow solution using Newton-Raphson method in rectangular coordinates. Okay. The minimum number of simultaneous equations to be solved is dash. How many number of equations we have to solve? How many number of equations we have to solve? Let's move. Total number of buses are 183. How many slack we have? We should check. How many PV? How many PQ? Check back to this one. PQ buses are 150. PQ are 150. 32 PV. Remaining one will come in the category of slack. Remaining one will be coming in the category of slack. Tell me, please. Tell me. How many equations we have to solve in the rectangular coordinates method? Number of equations to be solved. Equations to be solved in NR rectangular coordinates. NR rectangular coordinates. What is that formula? 2n minus 2. That's what we discussed till this point, right? 2n minus 2. 2n minus 2 means 2 into 183 minus 2. How much is this number? 2 into 183 minus 2. It will be 364. 364, you can say. So your answer will be obviously B. You can say answer is B. Answer will be B. Yeah, next. How many number of equations we have to solve in NR polar coordinates? NR polar coordinates, how many equations you have to solve? Anybody? Please tell me. I'll show in the next slide. NR polar coordinates. Number of equations to be solved in NR polar coordinates. NR polar coordinates. See, actually, in case of NR polar coordinates, we should find how many real powers you know. N minus 1 real powers. How many reactive pores you know? NPQ. That's it. What is the n minus 1 number? It's 182 plus how many numbers we have NPQ? 150. So it will be 332. That will be 332. Clear? 332 number of equations you have to solve in NR polar coordinates. Okay, next thing. How many equations you have to solve in the GS method? Number of equations to be solved in GS method. Number of equations to be solved in Gauss-Seidel method. Tell me anybody. How many equations you have to solve in the GS method? Today only we discussed, no? Gauss-Seidel method. How many equations you have to solve in that? Nobody is answering. N minus 1, right? We are calculating voltage only. Voltage equations you have. How many voltage equations you have? N minus 1. Except the slack bus, remaining all buses voltages you have to get. So it will be simply n minus 1. N minus 1 number of equations you have to solve in GS. So it will be 182 equations. 182 equations. Now, in your view, you tell me, in comparison between GS and NR, which method will take higher time to conduct one iteration? To conduct one iteration, which method will take the highest time? Which method will take the highest time to perform one iteration? Obviously, NR method, because number of equations to be solved are very high here. NR method is going to take a large amount of time to conduct only one iteration, whereas GS method will take very less amount of time because number of equations to be solved in GS method is very less compared to NR method. Getting all of you? Yeah, good. Less amount of time taken by GS method. Less amount of time per iteration is GS method. Okay, next thing. Let's continue with the polar coordinates method only. I think it is sufficient for the rectangular coordinates. Maximum they will ask the Jacobian size. So in the what we call polar coordinates, how will be the Jacobian elements that I am going to take up? Just I will show one PDF slide to you. How will be those Jacobian elements, and that I will show, and I will be picking up some conclusions from it. Okay, yeah. So I'll say Jacobian elements. Jacobian elements in NR polar coordinates method. NR polar coordinates method. Rectangular coordinates method we are not going to consider further. We are going to take up only NR polar coordinates method. Yeah. So let's say first of all, you know this delta P, delta Q. Okay, and I'm showing the Jacobian submatrices here. J1, J2, J3, J4 submatrices multiplied with delta mod V. Vector delta mod V. Okay, now listen please, listen. So I'm saying I'm not discussing these elements calculation in detail. I'm not going to discuss about these elements calculation in detail. Just listen, whatever I am saying, that will be sufficient, and how we are going to extend this method to further. Okay, listen. See, actually, while we are doing these calculations of J2 elements, particularly J2 elements, in a mathematical simplification, it is required to multiply these J2 elements with mod V. We have to multiply the J2 elements with mod V in order to get some mathematical simplification in the calculation of those elements. Similarly, J4 also required to be multiplied with mod V in order to get the mathematical simplification. Okay. See, as you multiply this J2 with mod V, J4 with mod V, original equations got disturbed, right? Original equations got disturbed. To avoid that, I have to divide this delta mod V with mod V numbers. Delta mod V by mod V we have to consider. Then if you consider delta P, which is J1 delta delta plus J2 into mod V into delta mod V by mod V cancel, you get J2 delta mod V. Similarly, second equation also remains same. Okay, if you want to write the statement to get mathematical simplification in J2, J4 elements calculation, J2, J4 elements calculation, it is required to multiply these matrices, with mod V. It is required to multiply these matrices with mod V. Clear? Okay, I will show that slide. Yeah, so you go through this one. Go through this. I will share this file to you in the Telegram. Just listen. This is the original NR method formulation. We have J1, J2, J3, J4, delta, 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 mod V. Delta, 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 mod V we have. Okay, J1 matrix is consisting dou P by dou delta elements, dou P by dou delta. And I was interested to get two elements here. Two elements. One, differentiation of real power with respect to own bus voltage angle. So called dou Pi by dou delta I, one number. Dou Pi by dou delta I, one number. Next number we are interested to get is dou Pi by dou delta K, differentiating the real power with respect to other bus voltage angle. Okay, next. Elements of J2 will be dou P by dou mod V. Dou P by dou mod V. Again, differentiating the real power with respect to its own bus angle. Right? Dou Pi by dou Vi, you can say. Dou Pi by dou Vi. And next term will be dou Pi by dou Vk. Dou Pi by dou Vk. Similarly, we should think about J3 and J4 elements also. J3 and J4 elements. Okay. See, listen. Whatever the thing required in the view of examination, as well as for the understanding. That only I am going to consider. Further. Actually, after making these changes, I will be calling this matrix as H. I will be calling this matrix as N. This matrix I will call M. This is L. H, N, M, L. Like this, we are going to name these matrices. Okay. So I'll show in the next slide. So it's a delta P, delta Q. So here I can say H, N, M, L submatrices. And this is delta, delta mod V by mod V. Delta mod V by mod V. Okay. Just listen here. Elements of H I am writing now. Elements of H. Directly I am saying HII. It will come like, just let's look at this one. HII is nothing but dou Pi by dou delta I na. So this is a HII. Minus Vi square Yii sin theta I minus Qi. Minus Vi square Yii sin theta I minus Qi. This is a HII. HIK means differentiation of real power with respect to the other bus angle. That will come like minus Vi Vk Yik sin of theta ik plus delta k minus delta I. Like this, you will get the elements of H. Elements of H. Next, elements of N. Elements of N. Yeah, you no need to write. No need to write. Just observe. Just observe the thing, whatever I am going to say. These equations and all not required to remember. Not required to remember. The final conclusion, what I am saying, that we have to be clear. Elements of N. Elements of matrix N. First, I will say NII. NII element. Yeah, let's look. Let's look into this NII element. It will come like VI square YII cos theta II plus PI. VI square YII cos theta II plus real power PI. And NIK, it will come to be VI VK YIK cos theta IK plus delta K minus delta I. Like this you will get. Cos theta Ik plus delta K minus delta I. These are the elements of N. Next, elements of M. Elements of matrix M. Again, two elements I will take up. MII one element. MIK is a second element. Let's look back. It's a J3 elements minus VI square. Okay. So it will come this equation only. This equation only we are going to get. But here we keep minus VI square. Minus VI square. And that's it. Okay. Next, MIK if you write, it will come negative of NIK. Negative of NIK. Right? Like this you can get. Minus of this. Minus of NIK. Minus of NIK. Next. Last, L matrix, I will say. L matrix. Elements of L. Elements of L matrix, I can say. First, LII will come like minus VI square YII sin theta II plus QI you get. Plus QI. Whereas if you calculate LIK, it will come like minus VI VK YIK sin of theta Ik plus delta K minus delta I. So it will be coming like what we call HIK. LIK and HIK will be coming equal. LIK and HIK will be coming equal. So like this we have these elements. HNML elements. Okay, now let's say one conclusion first. After that, we will extend. See, actually, what the elements in this matrix H is going to represent for you? What will be the elements in the matrix H represents for you? Tell me. It is representing dP by d delta, right? What do you mean by dP by d delta? Synchronizing power coefficient. dP by d delta is nothing but synchronizing power coefficients. So simply what I can say is, the elements in the H matrix gives the information about steady state stability of the system. Elements in the matrix H will give information about the steady state stability of the system. That's the first statement you have to consider. Elements in H matrix gives information about steady state stability. Steady state stability of the system. Gives information about steady state stability, particularly you can say angular stability. Angular stability under steady state operation, because it is dou P by dou delta. It's a synchronizing power coefficient. Okay, next. If you look at the L matrix is giving dou Q by dou V or dQ by dV. It's going to tell about the voltage stability of the system. Okay, so you write H is nothing but dp by d delta. That's why we said the above statement. Whereas elements in L matrix, elements in the L matrix gives information about voltage stability. Gives information about voltage stability. About voltage stability. Voltage stability of the system. And what that L is indicating here? This is dq by dV. It's indicating differentiation of reactive power with respect to the voltage magnitude. Okay, so kindly complete this one. Kindly complete this one. After this, I will tell something about whole Jacobian matrix. Overall, whole Jacobian matrix will say. So once after completion, you can raise your hands, please. Yeah, done. Look here. Here. See, for example, while we are doing this Newton-Raphson method of load flow, at some point, at some iteration, the Jacobian inverse was not existing, let us say. Jacobian inverse was not existing. Actually, what's the procedure actually is, listen please. First, we should calculate the power mismatches, Jacobian matrix, Jacobian inverse into power mismatches will give corrections. These corrections we should add to previous states. We get the updated angles and mod v values. With those updated states, again you find out the mismatches, Jacobian matrix, J inverse into mismatches will give again corrections. Add these corrections to previous states, we get the new states. Like that, we have to move ahead up to the point where we are going to make the convergence. Means in each and every iteration, we have to invert a big matrix here, so called a Jacobian. Okay, so if the Jacobian inverse does not exist, what's the conclusion we have to give? Yeah, if Jacobian matrix inverse does not exist, what's the meaning of this now? If the J inverse does not exist, J inverse does not exist means any other name you can say for this statement. J inverse does not exist means what? Determinant of Jacobian matrix equals to 0, you can say. Or determinant of Jacobian matrix equal to 0. Or determinant is 0. One thing. Next, any other meaning. Or Jacobian is a singular matrix. Jacobian is a singular matrix. Singular matrix. Or what's the other thing you can say? Jacobian is a singular matrix. I think you have some idea about eigenvalues. Eigenvalues of a matrix, right? One of the eigenvalue of this Jacobian matrix is 0. One of the eigenvalue of the Jacobian matrix is 0. Then obviously J inverse will not exist. Or one of the eigenvalue of J is 0. J is 0. Then see, all these statements will be same. All these statements will be same. Then the conclusion what we are going to make here is system is unstable. System is unstable. Okay. Then system is unstable. If anything happens, we can say the system will be unstable. This is one conclusion what we can make from the Jacobian matrix calculation. Jacobian matrix calculation. Okay. Yeah. Next thing. So I will move in the next slide and I will tell regarding Y bus elements little bit. Y bus elements. The next slide. Look here. Y bus element YIK, Y bus element. We have written it earlier in the polar form, like modulus of YIK at an angle of theta ik. Mod YIK at an angle of theta ik we have written. And we have to consider real part and imaginary part of this. What is the real part of this one? Mod yik cos theta ik is a real part plus j. Imaginary part will be mod yik sin theta ik. Like this, you can say real and imaginary parts. Mod yik cos theta ik plus j mod yik sin theta ik. This is real part. You can call it as gik. And this is imaginary part. You can call it as bik. Names: conductance, susceptance. Conductance and susceptance. Yik element will be expanded in the rectangular form. Real part is called as conductance. Imaginary part is called as susceptance. Okay, just listen. If XYR ratio of system is large, XYR of system is large value. XYR of the system is large value. See, if XYR of the system is large, in bracket you write R is very, very low compared to X now. R value was very, very low compared to X. Generally, you write the impedance as R plus Jx here. Impedance, you can write it as R plus Jx. And what is the admittance here? What will be the admittance? 1 by R plus Jx, you can write admittance. Admittance will be 1 by R plus Jx. And this you can write by doing that inverse or by using that complex conjugate. Complex conjugate, you will get it as R by R square plus X square minus J X by R square plus X square. Like this you will get after applying the complex conjugate. After applying complex conjugate, you will get this like R by R square plus X square minus J X by R square plus X square. Real part is called as conductance. Imaginary part is called as susceptance. That's the general thing. Tell me now, if the XYR of the system is very, very large, XYR of the system is very, very large, how is the value of G compared to B? How will be the value of G compared to B? Tell me please. How will be the value of G compared to B? Very low. That number G is very, very less compared to B. Yes or no? G is very, very less compared to B for a large, for high expiration system. Yeah, please respond. Yeah, G is very low. This you keep in mind. Let's move to the elements of HNML. Elements of HNML. Just look here. H elements, you see, H elements. It is Vi square, Yii, sin theta I. What you write is Vi square, sir, Yii, sin theta I. What you can write that Yii, sin theta I. That is the value Bii. Yii, sin theta I is nothing but the value Bii. Imaginary part of Y bus elements. Imaginary part of Y bus elements. Yes or no? Right. Next thing. You see in this matrix of n, Yii cos theta I you have. This is nothing but Gii, real part of Y bus element. Real part of the Y bus element. Here also. Yii cos theta I means a real part of the Y bus element. And in this matrix, Yii sin theta I, nothing but imaginary part of the Y bus element. Imaginary part of the Y bus element. Okay, one very simple question again. For a high expire ratio systems, how is the real part of Y bus element compared to imaginary part? How will be the real part of the Y bus element compared to imaginary part? Is it low or high? Real part of Y bus element compared to imaginary part. It will be very low. It will be very, very low. Very, very low. Okay. Now you observe now. Observe here. In this H element depends upon imaginary part of Y bus. H element depends upon the imaginary part of the Y bus. Whereas N element depends upon the real part of the Y bus. As a real part of Y bus is very, very low, definitely we expect elements in the matrix N are negligibly small compared to elements in M. Sorry, elements in H. All of you getting it or not? Tell me please. Tell me please, are you getting it or not? Elements in H depends upon the imaginary part. Elements in N depends upon the real part. Real part is very less compared to imaginary. Following. So by that way, elements in N are negligibly small compared to H elements. That's one conclusion. Similarly, you can get another conclusion with respect to these two matrices. I'm explaining again. M matrix. Elements depends upon the real part of I bus, which is negligibly small. Real part of I bus negligibly small. Whereas L elements depends upon the imaginary part of I bus, which is very high. Which is very, very high. So in that sense, elements in the matrix L are very, very large compared to elements in M. Or elements in M negligibly small compared to elements in L. For what cases these statements are valid? Only for high X by R ratio systems. Means my intention is to tell you now, for high X by R ratio systems, the values in N and M can be negligibly small. Negligibly small. So you can keep these matrices simply zero. Simply zero. And you can continue the method further. That method we are going to name it as decoupled load flow method. Decoupled load flow method. Okay. So I'll say in the next heading, decoupled load flow method. Decoupled load flow method. Load flow method. So you can say DLF method here. First statement I am saying now. First statement. Just look back to the elements what I have discussed till now. What the elements of H representing? All of you tell me please. What's the elements of H representing? Dou P by dou delta. Elements of N representing dou P by dou mod V. Means what we can say is the real power is more sensitive with respect to angle variation, and it is less sensitive with respect to voltage variation. That's why we are getting elements in N negligibly small compared to the elements in H matrix for large X bar ratio systems. Okay, so I'll say here first for large X bar ratio systems, large X by R ratio systems. First statement, elements in R, right first. P is real power is more sensitive to delta variation, and P is very less sensitive to mod V variation. Okay, that implies elements in matrix N are negligibly small, are very low compared to elements in H matrix. Elements in the H matrix. Yeah, we'll complete it by 12:40, 12:45. Pramod, we'll complete it by 12:40 or 12:45. Yeah. So that implies you can say the elements in N can be assumed as 0 for them. Elements in the matrix N can be assumed as 0 further. Okay. Next statement. With respect to reactive power, if you talk. Elements in M is representing dou Q by dou delta. L is representing dou Q by dou V. So L is very large compared to M elements. Means reactive power is more sensitive with respect to voltage variation, less sensitive with respect to the angle variation. So Q is more sensitive to mod V variation, and Q is less sensitive to delta variation. Okay, so that implies elements in M are very low compared to L. very low compared to L. Elements in M are very low compared to elements in L. So I can say the elements in the matrix M can be treated approximately 0. Elements in the matrix M can be treated approximately 0. Approximately 0. Okay. Now I will try to rewrite that matrix what we have taken. Let's call this matrix only. This matrix I am attempting to rewrite. Okay. So this is a relation now. This was a relation. Now we are going to keep this N and M matrices simply 0 without doing any calculation. Without doing any calculation, simply we make these matrices 0. 0. What's the first matrix you can get now? Delta P is equals to H into delta delta. Delta Q equals to L into delta mod V by mod V. Okay. So I'll say in the next slide. Delta P matrix is nothing but H into delta delta matrix. Then what will be the corrections in angles here? Corrections in angles will be H inverse into delta P. H inverse into delta P. And next matrix, delta Q is equals to L into delta mod V by mod V. Mod V. And you can write from this delta mod V by mod V vector will be coming like L inverse into delta Q. L inverse into delta Q. Okay. L inverse into delta Q. See, this is what the decoupling you can say. Actually, real power depends upon both angle as well as voltage magnitude. But we are removing the dependency of real power with respect to voltage. And we are saying that real power is sensitive towards only angle variation. Okay. Similarly, reactive power depends upon both as far as equation is concerned. Voltage magnitude and angle, but we are removing the dependency of reactive power with respect to angle, and we are saying that it is mainly dependent upon the voltage magnitude variations. What the advantage you are getting from previous NR method to DLF now? What's the advantage you are going to get between the NR method to present method? That is, matrix to be inverted, size of the matrix to be inverted. In the previous case, big matrix, H, N, M, L, that big matrix you have to invert. But here, sizes of the matrices to be inverted will be a bit small. H, L. What's the size of H? Anybody? What is size of H? N minus 1 by N minus 1. It's the size of H. What's the size of L? NPQ by NPQ. NPQ by NPQ will be the size of L. Matrix H size will be N minus 1 by N minus 1, we can say. Okay. Done. Next. I'll try to take up these H and L elements. Already we have written that I am going to rewrite H and L elements. Let me copy. These are the elements of H we have written already. Elements of H matrix. I will be doing some sort of expansion here. That's why I'm writing these things again. So it's BII here, and you have minus QI. This is a HIK element. HIK element. Let me expand this HIK element now. HIK I am going to expand. Just go through it. Minus VI VK. Look here, sine theta IK plus delta K minus delta I. So it's like sine A plus B. Sine A cos B plus cos A sine B. Sine A cos B plus cos A sine B. YIK to be multiplied. YIK to be multiplied. Mod YIK. Sin theta IK. Cos delta K minus delta I. One term. Second term. Mod YIK. Cos theta IK. Sin delta K minus delta I. Like this you will be getting. Mod yik sin theta ik cos of delta k minus delta I plus mod yik cos theta ik into sin of delta k minus delta. Like this you will get an expanded term. And you know this yik sin theta ik is a value bik you can write. And yik cos theta ik is a value gi. Okay, let me write. So it will be coming like minus vi vk magnitudes multiplied to bik cosine delta k minus delta I plus gik sin delta k minus delta I. Like this you can get hik element. Hik element. I have to make some more assumptions further. So let's take elements of L quickly. Elements of L. Elements of matrix L I am taking up quickly. Lii, if you take, it will come like minus Vi square Bii plus Qi, reactive power plus Qi. And Lik number will be same as Hik. Lik number will be same as Hik. Lik and Hik both will be same. Both will be same. Yeah. Now, listen. Look, very simple assumptions only. See, actually, if you compare this Bii and Qi, Vi square, how much first? I will do that comparison. First, Vi square, close to 1. Vi will be very close to 1, na? Maybe 0.95, 0.96, 1.01 like that. So, Vi square is close to 1. That's one confirmation. So, major term in this product is Bii. And you have Qi. Qi, Bii value will be generally in the order of 10, 20, 30 in that range. Bii will be in the order of 10, 20 like that. But Qi, reactive power, can we get 10 per unit reactive power, 20 per unit? May not be. So Qi value like 1 per unit, 0.6 per unit, 0.3 per unit like that. Means my intention is to tell you, in these two terms, Qi term is negligibly small. Qi term is negligibly small. So that in this summation, you can remove that Qi. And you can take this simply as minus Vi square Bii. Minus Vi square Bii. Same change you can make for this also. You can remove Qi in this summation and you can consider this simply minus Vi square Bii. That's one assumption. Okay. Next thing. Generally, delta K minus delta I angle. Angular difference between two near buses. It may be like 5 degree, 10 degree like that. Angular difference between the two buses will be, near buses will be 5 degree, 10 degree. If that's the case, cosine of angle will be very close to 1. Of course, here you have BIK. And you see this one, GIK very low. Sine of that angle is very less. I said sine angle also very less only. So this GIK into sine, this term is negligibly small compared to BIK. So that this can be neglected and this whole we can write it as BIK. After making all these assumptions, that method we are going to name it as fast decoupled load flow method. Okay? Yeah. So let's take the heading now. Fast decoupled load flow method. Fast decoupled load flow method. FDLF method. So assumptions I am writing first. Assumptions. First assumption. Qi is very, very less compared to mod Vi square into Bii. Qi is very, very less compared to Vi square into Bii. If that is the case, HII element, you can write it as minus Vi square into Bii. Lii number can also be written as minus Vi square into Bii. Like this you can say. Getting this? This is the first assumption. And now that HII, LII both are equal. HII, LII both are equal. Second assumption. Second assumption I am writing. Let delta K minus delta I is very low angle. Delta K minus delta I is a very low angle. Then cosine of that angle will be approximately 1. Cosine of that angle will be approximately 1. Okay. Yeah. So cosine of that angle is very close to 1, very close to 1. So that earlier, as we said, so GIK into sine of delta K minus delta I number will be very, very low compared to BIK value. BIK value. By making this assumption, HIK and LIK values will come to be, just look back, this will be minus Vi Vk and this whole is Bik. So minus Vi Vk Bik, that's it. Minus Vi Vk Bik. These are the approximate elements in the H and L matrices. These are the approximate elements in the H and L matrices. Okay. Now let's take equation 1, what we have earlier. Equation number 1 I will take first. The next slide. Set 1 means this one. This set. This one you say and this 2. Set 1. Set 1 I will try to rewrite now. Set 1. Delta P is equal to matrix H into delta delta. Matrix H into delta delta. Yeah. So I'm not doing this one in detail. I'm not doing this one in detail. Just observe my explanation what I'm going to make. This H na H, we have HII, HIK, and so on, HNN. These elements of H, I will be substituting these two things. HII you know already. HIK also you know already. Now we have to substitute the H elements. We'll get some voltage common in them. Listen please, listen kindly. We will get some voltage common. That we will take to the other side. So left side matrix will come to be delta P by mod V. Delta P by mod V. Whatever the remaining elements you have in the H, whatever the remaining elements you have in the H might be coming as one constant matrix B dash. That will be coming as a constant matrix as B dash. Not only that, you have some voltage magnitude also in this. We have some voltage magnitude also in this one that we are assuming as 1, so that this matrix B dash is treated as constant. B dash will be treated as constant. Very simple, very simple. H elements is consisting voltages, right? H elements are consisting voltages along with B elements. Remove the voltage out. Remove the voltage out. And what that H matrix is consisting now? Only negative values of imaginary parts of Y bus. Negative values of imaginary parts of Y bus. So this B dash matrix, it's a constant matrix now. Constant matrix. Why it is so means your Y bus is a constant matrix. So it consists negative values of imaginary parts of Y bus. Imaginary parts of Y bus. Negative values of imaginary parts of Y bus will be consistent. Okay. Similarly, set 2, how we are going to write? Set 2. Set 2. Set number 2. That set number 2 will be like delta Q equals to matrix L into delta mod V by mod V. Matrix L into delta mod V by mod V. And after making the modifications, like L elements, we have to substitute the elements what we have, LII, LIK, like that. And you take voltages common in the elements, voltages common, and some cancellations will go. And finally, this matrix we are going to get as delta Q by mod V vector is equal to, it will be B double dash into delta mod V, like this you can get. B double dash into delta mod V. And whatever the B double dash you said now, this will be consisting again negative values of imaginary parts of Y's. It's also a constant matrix. Consists negative values of imaginary parts of Y's. Imaginary parts of Y's. Negative values of imaginary parts of Y's. Yeah. Next thing. Listen, please. Listen, please. See, what is the advantage we are getting with the help of this FDLF method compared to previous one? What's the advantage? In the previous method, so-called DLF and FDLF, we have to calculate the matrices, right? In each iteration, we have to calculate the matrices. But in this FDLF method, whatever the B dash and B double dash you got, these are constant matrices. B dash and B double dash matrices are constant matrices. So it is not required to calculate these matrices in each and every iteration further, right? So B dash and B double dash are constant matrices. Need not to update constant matrices, and we no need to update them. Matrices. We no need to update them in each and every iteration. Okay, just I will tell you how to get that B dash and B double dash matrices quickly by taking some example. By taking some example, I will try to tell you how is that B dash and B double dash matrices. Is delta Q by mod V only. It's delta Q by mod V. Delta Q by mod V, and you don't have mod V in the delta V. You don't have that mod V in the delta V because that mod V what we have here and L will be cancelled out. And one more mod V you have that we are sending to other side. Yeah. See this? For example, I have a 4-bus system. 4-bus power system network I have. 4-bus power system network. In that, bus number 1, it's a PV. Bus number 2, it's a PQ. Bus number 3, it's a slack. Bus number 4, it's a PQ. It's a PQ. Like this, we have buses. Generally, we don't get any numerical question, Shilpa. Generally, we don't get any numerical question. Okay. Listen here. Tell me now. In this, again, we have to follow in the same procedure of NR method actually. Same procedure of NR method we have to follow. First, you write unknown states here. Unknown states. What are the unknown states in this case? Bus 1, delta we have to calculate. Bus 2, delta we have to calculate along with the voltage. Okay, slack, I no need to calculate anything. Bus number 4, I have to calculate angle as well as voltage. Angle as well as voltage we have to calculate. These are the unknown states. What are the equations now? What are the equations? Just look here. P1, P2, P3, P4. These are the equations here. Similarly, Q1, Q2, Q3, Q4. These are the equations, reactive powers. Right? Real power equations as well as reactive power equations. Tell me now, real power equations which we have to consider. Bus 1 we can consider. Bus 2 we can consider. Bus 3 we should not. Bus 4 you can consider. Reactive power usage. Q1 we can't consider. Q2 we can consider. Q3. Q4 we can consider. Q3 we can't consider. Like this we have to do as usual as we have done earlier. Okay. Now first set is delta P by mod V equals to B dash into delta delta. I have to show that. Okay. Yeah. Set number one. Delta P by mod V is equal to B dash into delta delta matrix. B dash into delta delta matrix. Now, what is the delta P by mod V consisting now? You should say delta P1 by mod V1, delta P2 by mod V2, and so on, delta P4 by mod V4. That's right. Delta P1 by mod V1, delta P2 by mod V2, delta P4 by mod V4. Okay, and you have B dash matrix. You no need to bother about this matrix. We'll write it in a very, very simple way, B dash. And you confirm what is delta delta now. What's delta delta? Delta delta 1, delta delta 2, delta delta 4. Delta delta 1, delta delta 2, delta delta 4. That's it. Simple. Delta delta 1, delta delta 2, delta delta 4. Okay, now these elements, first element you see, first element 1 1 1 1 means it is minus B11. Negative value of imaginary part of y bus na? Negative value of imaginary part of y bus means B11 negative. Next one 1 2 means it is minus B12. 1 2 minus B12. Next one 1 4 minus B14. Next 2 1 minus B21. 2 2 minus B22. 2 4 minus B24. Next year minus B41 minus B42 minus B44 minus B44. Like this, you will get the elements in the B dash matrix. Elements in the B dash matrix. That's the set one. Set one. Let's write set two. Set two in the similar way. Equation set two. Equations set number 2. That set 2 delta Q by mod V is equals to, you get this B double dash into delta mod V. B double dash into delta mod V. What you can get the delta Q by mod V? Delta Q by mod V means delta Q2 by mod V2. Delta Q4 by mod V4. Delta Q2 by mod V2. Delta Q4 by mod V4 is equal to, here you get B double dash matrix. It's very simple to write. I will take care of that. Delta V will be delta mod V2, delta mod V4. Delta mod V2, delta mod V4. What is this element? 2, 2, 2, 2 minus B22. Next, 2, 4 minus B24. Next year, 4, 2 minus B42. 4, 4 minus B44. Like that, you will get that B double dash matrix. B dash and B double dash matrices. Yeah. So all of you getting this? Tell me please. So this is a way how to write this B dash and B double dash matrices. Please tell me. Yeah, please tell me. How will be these two matrices B dash and B double dash? Whether these are symmetric or not? Symmetric. Whether these matrices are symmetric matrices or not? Yes. Because Y bus is a symmetric matrix. Na? As Y bus is a symmetric matrix, obviously B dash and B double dash will be symmetric matrices only to be considered. Okay. So I'll write now B dash and B double dash are square, symmetric, whether these are sparse matrices or not, in the view of big power system network. In the view of big power system network, whether these are sparse matrices or not. Yes, because Y bus is a sparse matrix. So obviously these are square symmetric sparse matrices. Sparse matrices to be considered. Square symmetric sparse matrices to be considered. Okay, next. Okay, let's think about the Jacobian matrix in the NR method. Jacobian matrix in the NR method. Just look here. In the NR method, Jacobian matrix. Is it a real matrix or complex matrix? That you tell me first. Jacobian matrix, is it a real matrix or complex matrix? Real matrix only. There is no complex number in that. It's a pure real matrix only because you don't find J symbol anywhere. You don't find the J symbol anywhere. So Jacobian is a real matrix. Real matrix. Okay. It's a real matrix. And is it sparse or not? Is it sparse or not? Jacobian, is it a sparse matrix or not? Tell me, please. Is it a sparse matrix or not? Nobody is responding. Tell me yes or no. See, observe here, we have discussed about H elements, right? H elements, N elements. HIK, look once. HIK depends on what? HIK depends on what? YIK. HIK depends on YIK. If YIK is 0, HIK also 0. If YIK is 0, HIK also 0. Means, how many YIK values are 0 for you? Off-diagonal elements. Large number. A large number of off-diagonal elements are 0. So obviously HIK number also comes to be 0. Means in the H matrix, many values in the off-diagonal will be 0s only. So H matrix is sparse. H matrix is a sparse. Similarly, N matrix. N depends upon YIK. NIK depends upon YIK. YIK, many values are 0. NIK, many values are 0. Similarly, MIK depends upon YIK. LIK also depends upon YIK. So as a conclusion, as a Y bus is a sparse matrix. Y bus is a sparse matrix. Your Jacobian matrix also comes to be sparse matrix only. Because HIK, NIK, MIK, LIK, these values are depending upon the YIK number directly. Okay. So real matrix, not only that, it's a sparse matrix. Sparse matrix. Okay. Yeah. So this ends the what we call load flow analysis almost. Left with one small topic, that is comparisons. Comparisons between the load flow analysis. Means GS method, NR method, FDLF method comparisons. I will send some notes for that. In that student portal only. I will upload that notes. Okay. It's very easy. Already we discussed some comparisons with respect to convergence time and all. That conclusion table I will be uploading you in the student portal. Okay. So if anybody have doubts, you can ask me now. Then write your hand. Yeah. So you can raise your hands. If anybody having a doubt, you can raise your hands. Bharat. Bharat, do you have any doubt, Bharat? No? Or else I will be available always on this number. Vaishnavi. This is my mobile number 96184-61918.
Hello, sir.
In these days, that's why I am unable to answer many of your questions. Whenever I am getting some time, I am about to answer your doubts and all. Okay. If you have any doubt, you can put WhatsApp or Telegram message to this number, or else you can call me also. Yes, sir. Okay, tell me, Vaishnavi, any doubt you have, Vaishnavi?
Sir, in 25 is page number, sir.
25. Okay. Tell me, Vaishnavi. Vaishnavi, are you there? If anybody have doubts, please raise your hands. Else we can close the session. For any miscellaneous problems overall, I will come to you. Manivanam, because buses are a bit close, so that we can say impedance between the buses might be very low. Means line impedance may be very low. That's the reason. I will meet your requirements mostly. Okay. Gobiraju, for the first time itself, it is a bit difficult to understand what I feel, particularly NR method and the Gauss-Seidel method. Okay, just you revise the thing. I will be available in this mobile number, as I said you, right? You can contact me to this number. Wherever you get a doubt, you can ask me in that. Okay. Okay, Vaishu, you just put a request to me to the Telegram number. Vaishnu, you please your request to that number what I said. Okay. Yeah, put a request, Dwarkesh, to this number, Telegram number. You can put a request. I'll add you. Yeah. Okay. Yeah, you please come to online. Naresh Kumar. Tell me, Naresh Kumar.
Sir.
Tell me, Naresh.
Sir, can you please send me the solution for additional question PDF, sir?
I will send. Actually, I had it, but I have to search and I will send. I will send maybe tomorrow. Surely.
Okay, sir. Thank you, sir.
Okay. Tulsi.
Hello, sir.
Tell me, Tulsi.
Sir, in 26F, sir.
26. Okay.
Sir, shunt reactors ni adi enduku
Fixed
తీసుకుంటాం?
shunt reactor. It's a fixed shunt reactor, na?
Yes, sir.
It is unable to maintain the terminal voltage as constant.
Okay, sir.
Even though fixed shunt capacitor, it is unable to maintain the terminal voltage as constant.
Okay. That's why we are considering it as PQ bus.
PQ bus, yes. It's
Sir,
like
another-
just shunt impedance. We will put that into Y bus.
Okay, sir.
Mm-hmm.
Sir, another doubt, sir. Gauss-Seidel method లో మనము వోల్టేజ్ కనుక్కున్న తర్వాత ప్రీవియస్ వోల్టేజ్ ని కన్సిడర్ చేస్తున్నాం కదండి సార్ మాగ్నిట్యూడ్ లో.
Yeah.
అప్పుడు మళ్ళీ మనం ఇటరేషన్స్ చేస్తున్నప్పుడు వోల్టేజెస్ ఇంకా సేమ్ గా ఉంటాయి కదండి సార్. అప్పుడు ఎర్రర్ అనేది మనకు 0 వస్తుంది కదండి సార్.
Voltage magnitude will be same, but angle will change, na?
Yes, sir.
We have to take difference between voltage to voltage, not magnitude difference.
Okay, both angles.
Angles has to be considered in the voltage difference, right?
Okay, sir.
Okay.
Okay, thank you.
Manikanta.
Sir.
Tell me, Manikanta.
నాకు సిమెట్రికల్ కాంపోనెంట్స్ లో డౌట్ ఉంది సార్.
చెప్పండి.
బ్యాలెన్స్డ్ అన్బ్యాలెన్స్డ్ సిస్టమ్ ఇచ్చి వోల్టేజ్ ఇచ్చాడు సార్, లైన్ వోల్టేజెస్.
ఓకే.
బట్ ఫేజ్ బి వోల్టేజ్ కనుక్కోమన్నాడు సార్.
Okay. You first
అప్పుడు
convert those line to line voltage to symmetrical components.
నేను మామూలుగా సిమెట్రికల్ కాంపోనెంట్స్ లో కన్వర్ట్ చేశాను సార్.
Hmm.
కన్వర్ట్ చేసి సిమెట్రికల్ కాంపోనెంట్స్ ని మళ్ళీ ఫేజ్ లో కన్వర్ట్ చేయాలి కదా సార్.
Yes, you have to convert.
కన్వర్ట్ చేసినప్పుడు యాంగిల్ -j/√3 అని వేస్తున్నారు సార్ అక్కడ.
Minus J by
-j/√3 ఇంటూ లైన్ వోల్టేజ్ అని వేస్తున్నారు సార్. అది సిమెట్రికల్ కాంపోనెంట్ వోల్టేజ్. బట్ నాకు అనాలిసిస్
అట్లా
ప్రకారం
ఉండదు. మీ సొల్యూషన్ నాకు పంపించండి ఒకసారి.
సార్ నా అనాలిసిస్ ప్రకారం పాజిటివ్ సీక్వెన్స్ లైన్ టు లైన్ వోల్టేజ్ ఈక్వల్ టు √3 ఇంటూ పాజిటివ్ సీక్వెన్స్ ఫేజ్ వోల్టేజ్ అట్ అన్ యాంగిల్
Plus 30
30 degrees వచ్చింది
Hmm.
సార్.
మీరు ఒకసారి మీ సొల్యూషన్ పంపించండి, వాళ్ళు ఇచ్చిన సొల్యూషన్ ఒకసారి పంపించండి.
ఓకే సార్.
ఓకేనా?
ఓకే సార్.
Okay.
అనదర్ డౌట్ సార్.
give me.
ఇనీషియల్ ఒక యాంగిల్ దగ్గర ఒక పవర్ ఇచ్చాడు సార్.
Okay.
అండ్ నెక్స్ట్ ఒక సమ్ లోడ్ అనేది చేంజ్ చేసే అన్నాడు సార్.
Hmm.
లోడ్ చేంజ్ చేసి న్యూ ఈక్విలిబ్రియం పొజిషన్ యాంగిల్ కనుక్కోమన్నారు సార్.
Okay.
అప్పుడు నేను ఒకవేళ ఇప్పుడు సింక్రనైజ్ పవర్ ఈక్వేషన్ ఉంది చూడండి సార్.
Hmm.
P of delta naught plus del delta plus minus P of delta naught equal to
Hmm.
P max cos delta naught into del delta radians ఉంది కదా సార్.
Hmm.
ఆ ఈక్వేషన్ ప్రకారం సాల్వ్ చేస్తుంటే ఆన్సర్ రావట్లేదు కదా సార్ మరి.
No, initially we have some load, you said.
ఇనిషియల్లీ సమ్ హ్యావ్ 40 మెగావాట్ సార్
40 megawatt load ఉంది. Okay.
లోడ్. నెక్స్ట్ ఇప్పుడు లోడ్ ఈస్ చేంజ్డ్ టు 45 మెగావాట్.
Okay.
లోడ్ ఈస్ చేంజ్డ్ టు 45 మెగావాట్. ఇన్ దట్ కేస్ న్యూ ఈక్విలిబ్రియం పొజిషన్ యాంగిల్ ఈజ్ అన్నాడు సార్.
మీరు ఆ 45 మెగావాట్ డైరెక్ట్ గా ఈక్వేషన్ లో సబ్స్టిట్యూట్ చేసి డెల్టా కనుక్కోవచ్చు కదా.
ఎస్ సార్. నేను
మళ్ళీ డెల్టా అవన్నీ ఎందుకు మీకు ఇంకా?
ఈక్వల్ ఏరియా క్రైటీరియా మెథడ్ నుంచి ఒక వేలో సాల్వ్ చేయొచ్చు సార్ మనం.
ఈక్వల్ ఏరియా క్రైటీరియా మెథడ్ ని సాల్వ్ చేయొచ్చు. ఓకే.
ఒకవేళ నుంచి ఈక్వల్ ఏరియా క్రైటీరియా మెథడ్ నుంచి ఒక వేలో సాల్వ్ చేయొచ్చు సార్. ఇంకో వే
ఈక్వల్
ఏంటంటే
ఏరియా క్రైటీరియా మెథడ్ యూజ్ చేసిన తర్వాత మీరు సిస్టమ్ స్టేబుల్ అన్స్టేబుల్ చెప్పగలరు అంతే. ఫైనల్ స్టేబుల్ యాంగిల్ చెప్పలేరు కదా ఈక్వల్ ఏరియా క్రైటీరియా ద్వారా.
ఎస్ సార్.
ఈక్వల్ టు సే వాట్ ఇస్ ద ఫైనల్ స్టేబుల్ యాంగిల్ యూ హావ్ టు యూజ్ పవర్ ఈక్వేషన్ ఓన్లీ.
కానీ అక్కడ పవర్ ఈక్వేషన్ ఉపయోగించకుండా ఓన్లీ ఈక్వల్ ఏరియా క్రైటీరియా ఉపయోగించి ఒక ఫార్మాట్ వస్తుంది సార్. నాన్ లీనియర్ ఈక్వేషన్ వస్తుంది సార్ అక్కడ.
ఓకే.
నాన్ లీనియర్ ఈక్వేషన్ వస్తే ఇప్పుడు మనం ఇందాక బై టైలర్ సిరీస్ ఎక్స్పాన్షన్ వేసాం చూడండి సార్.
అదేనన్నా ఇప్పుడు ఫైనల్ గా ఆ ఎక్స్పాన్షన్ అయినా అదే వస్తుంది, ఇదైనా అదే వస్తుంది ఆన్సర్. కానీ ఆ ఎక్స్పాన్షన్ వచ్చే ఆన్సర్ అప్రాక్సిమేట్ ఆన్సర్.
రెండు ఈక్వల్ రావట్లేదు సార్.
రావు, అదే చెప్తున్నా నీకు. ఆ ఎక్స్పాన్షన్ చేయడం వల్ల వచ్చే ఆన్సర్ మీకు అప్రాక్సిమేట్ ఆన్సర్ అవుతుంది. ఎందుకంటే మీరు ఆ ఎక్స్పాన్షన్ చేసినప్పుడు ఆ డెల్టా తీసుకున్నారు, మరి డెల్టా స్క్వేర్ డెల్టా క్యూబ్ అవి తీసుకోలేదు కదా. హైయర్ ఆర్డర్ టర్మ్స్ నెగ్లెక్ట్ చేస్తున్నారు కదా మీరు. నెగ్లెక్ట్ చేస్తున్నారంటే ఆ విధంగా వచ్చే ఆన్సర్ అప్రాక్సిమేట్ ఆన్సర్ అవుతుంది మనకి.
ఓకే సార్.
ఓకేనా?
ఓకే సార్.
ఇంకా ఎనీ అదర్ డౌట్ హియర్ మణికంఠ?
ఇంకొకరు అడగండి సార్. డౌట్స్ ఒక దాంట్లో రాశాను సార్, కొంచెం అందులో
ఓకే. సాయి చరణ్ రెడ్డి.
Hello.
Tell me, Sai Charan.
Sir, can you please take an example of any some bus system? Give us some examples today.
Which example?
You open that slide, anyone slide. Anyone, sir. 6-bus system or 4-bus system.
Okay.
You took now
Okay.
example. Sir, if you open that, I can tell my doubts. That's why.
Okay, I have 10 bus system. Tell me.
In those 10 buses, have various like PV and PQ.
I am unable to listen to you, Sai Charan. So make your audio perfect.
Sir, in that we have buses and PQ buses, like 4 of them PQ, like 5 of them are PQ buses. Now, in our method, that complex form, sir, that rectangular form. You told that for every like every equation we should find real and imaginary na, sir, for
Yes,
V
yes.
and for delta.
Hmm,
Then in some cases we don't know for PQ we don't know delta 1 and V1 both we don't know na, sir.
Okay.
For both of
Yes.
them A1 and B1 AI and BI will be common, no, sir.
A and B we have to calculate. Yes.
Both are common na, sir. Here the unknowns are two only for two of them.
Two only. That's what I also said, Sajan. Two only. Unknowns will be two.
Then in our analyzation we took those will be every instant those will be double na, sir. According to that only we did that.
Double only. Even if it's a PQ bus or PV bus, you have to calculate two unknowns.
Also, I'm telling that for PV bus we did not calculate.
So I'm unable to listen to you, Sai Charan.
Hello, sir.
Tell me, Sai Charan.
Sir, for PV bus we should not call we not calculate V sir, here.
No, you have to calculate angle for PV bus. That's why you have to calculate real and imaginary parts.
Okay, sir. In PQ bus we should
PQ bus, you
calculate
have to
both of
calculate
them, na,
both
sir. V
voltage
and
magnitude and
delta.
angle. Voltage magnitude and angle. So there also you have to
Then
calculate real part and imaginary
then
part. That's it.
so if you calculate once it is enough, na, sir. For
That's it. That's what
if you say
I am
the
also saying.
ith bus.
That's what also I am saying you.
Uh,
Two quantities only I have
okay,
written
okay,
at
sir.
PQ bus also, right?
Okay, sir. Okay, sir.
Okay.
Yes, sir. Yes, sir.
Yeah. Any other doubt you have, Sai Charan?
Sir, we don't have many problems on this topic, no, sir. The load flow analysis topic.
Load flow
Like
analysis,
the
we don't have many numerical
yes, sir.
problems. They used to ask theory questions.
Yes, sir. Okay.
That's it, Sai Charan?
Thank you. Yes, sir.
Yeah. Swapnil.
Hello.
Tell me, Swapnil.
Yes, sir. Sir, actually, I have one doubt on the stability in the numerical. Sir, actually, I sent it on the WhatsApp, sir.
WhatsApp or Telegram?
WhatsApp, sir.
Just now you said?
No, sir. Actually, at 11:30, just the an alternator floating on the.
No, okay.
Sir,
See,
I did
initially
not get.
you take zero powerful initially.
Yes, sir. Then we can get the angle as a 0, sine
Initially
delta.
0, then
Yes.
we have to make a sudden rise in the power.
Yes, sir.
So it's a power angle curve, na?
Yes, yes, sir.
This is your initial PS1 equals to 0.
Yes.
This line.
Yes,
And
sir.
suddenly we are increasing this power to a value PS2, something like this.
Yes, yes, sir.
And acceleration will start. This is the initial operating point.
Yes, sir.
And this is the area which we are going to cover.
Yes,
A1
sir.
area.
Sir,
And this
actually,
is A2 max area.
yes, yes, sir.
And we should get exactly speed equals to synchronous speed at this point X.
Yes, sir.
That particular PS2 is called as sudden rise in the power required.
Yes, sir. But sir, when we are going to solve this numerical by using swing equation, sir, that
You will
time
get a
we
nonlinear
getting.
equation there.
Yes, sir. We getting two variables, sir.
By using those two variables, will be having some relation again, right?
No, sir. Actually, sir, suppose we calculate from integration of del is equal to 0 to del is equal to max, and we got del max one variable, and
Del max
PM
is
is
what?
also.
Del max is what? 180 minus delta 1.
Okay, sir.
This
Means
is delta 1.
okay, so we have
Delta
to take
1
up
is
to
unknown.
180. Okay. Delta 1 is unknown. So, sir, there will be delta 1 is one variable, and they also did not give the mechanical power also now. So
What is
there are
mechanical power?
they did not provided that data. Means
What is it? What is it?
means sir, they asking that we have to calculate the mechanical power we can
Okay.
suddenly increase.
Ah.
Yes, sir. So there are two variables. So I
Which
did
are two
not get how.
variables?
Del also we have to find. How we can find del?
What is
Del one.
PS2? What is PS2?
PS2, sir, means where our system will be stable after some time. That na?
P maximum sine delta 1, na?
Yes, sir.
That's the relation again between PS2 and delta 1.
Okay, sir. And
That
sir,
you
how to
substitute
find?
and you get only one delta, one unknown.
Okay, suppose sir, we have to just integrate this PS2 minus P max sine delta 1, na?
P max
Means
sine
sorry.
delta.
Yes, P
PS2
mechanical
minus P
minus.
max. P maximum sine delta.
Yes, we have to integrate
Starting
0
from
to.
0 to 180 minus delta 1. That we should make
Yes.
it equals to 0.
Okay.
That's
And
it.
suppose sir. Okay, and sir here.
By trial
Okay,
and
they
error method,
given
you
P
should
max
get delta
value.
1. By trial and error method, you should get delta 1.
Yes, sir. So there are two variables, so that's why I'm asking.
Only one variable now.
Sir, PS2 and delta, sir. Suppose sir,
That's what I said familiar here. PS2 you can replace with P max sine delta 1, right?
Okay.
Then you
Sir,
get only
suppose
one
we
variable
replace
delta 1.
okay. Sir, it
You get
will
only delta
cancel
1.
na, sir, PS2. Sir, suppose we put PS2 we put here, it will become P max sine delta 1 and here P max sine delta, then it will cancel. There is subtraction sign. There is a subtraction. There is subtraction, sir. So.
Okay, subtraction is there. Then.
So it cancel na, sir.
What is left side term?
P max sine delta 1.
What is this one?
Okay, sir. Oh, it is sine delta. Okay, sir. Okay, got it.
Okay.
Sir. Yes, sir. Okay, thank you.
Sai Charan, do you have any doubt more? Please raise your hands. Tell me, Sai Charan.
No, sir. No, sir.
Yeah. Any more doubts? Please raise your hands. Swapnil.
Yes, sir. Sir, sometime I have doubt. So, sir, where should I send? Means on the WhatsApp or Telegram? Because sometimes
Telegram or
Telegram you
WhatsApp?
are
Anything. Telegram or
sometime you are
WhatsApp?
not active and Telegram. So that's I am asking.
Telegram, I will be active only.
Okay, sir. Then no.
Only, but I will see occasionally some time I will set and I will be looking in that time only.
Okay, sir. Okay, thank you, sir. Thank you.
Okay. Any more doubts? Please raise your hands, else we can close the session. Vaishnavi. Vaishnavi.
Hello, sir.
Tell me, Vaishnavi.
Sir, in 25 page, sir.
Tell me what you have doubt in that.
Sir, in that why shunt capacitors and shunt reactors are considered as PQ bus?
After keeping shunt capacitor bank, are you sure that voltage magnitude is constant at that bus always?
No, sir.
Because you don't have a control, right?
Yes, sir.
So if you don't have a control, you should not treat that in the PV bus category.
Okay. Okay, sir.
Shunt capacitor, I know it will improve the voltage. That's okay.
Yes, sir.
But is it possible to maintain that voltage constant or not? That's the question.
We cannot maintain constant.
Can't. But if there is a controller along with the capacitor bank, then it is possible to maintain the voltage as constant by using the control strategy.
Okay. If we control, then we have to consider them as PV.
PV bus. PV, yes.
Okay, sir.
You say if there is a controlled capacitor bank, controlled reactor bank, then it's a PV bus.
Okay, sir.
Okay?
Okay, sir. Okay, sir.
Any other doubt here, Vaishnavi?
No, sir.
Yeah. Any more doubts? Please raise your hands. So I think nobody's having a doubt. So I'm closing this session. Thank you. Syllabus is over by this point. F and S syllabus is over by this point. Okay.